speaking. Okay. I'll be speaking about young, roughly 1 million-year-old pre-main sequence stars called T-Tauri stars. T-Tauri stars are accreting material from their surrounding protoplanetary disks. The UV is the best tracer of accretion in these objects. And I'll be discussing how, by comparing UV observations with data at longer wavelengths that trace the disk, we can learn more about the connection between the young star and the innermost regions of the protoplanetary disk. So I'm going to be focusing on variability and the star-disk connection. And I've structured the next 14 minutes around these 3 questions. The first serves as a quick intro, very quick recap of the field. The second, I'll spend most of my time here telling you about our pilot study, a simultaneous multi-wavelength observing program of 1 T-Tauri star. And for the last question, I'll go into directions for future work on accretion and accretion variability. So before getting to variability, how does accretion proceed in these young systems? So we have the protoplanetary disk around the young star. The disk goes out to hundreds of AU. It's made up of gas and dust. Somehow, via some unknown mechanism, that material moves inward towards the star. There's a hot inner dust wall where the temperature in the disk gets hot enough for the dust to sublimate. And then going inward from that, there's only gas that goes inward towards the star. Now, these young stars have strong magnetic fields, and the magnetic field lines truncate the inner gaseous disk, and material is channeled onto the star via the magnetic field line, and it shocks on the surface of the star. So from the accretion flow, when the material is in the accretion flow, we observe broad emission lines in the optical and the near infrared. And when the material impacts the surface of the star, this region is very hot, 8 to 10,000 Kelvin. And so we see a very hot continuum, hot UV continuum. And then there's also ejection from the system, disk winds and jets, but it's not clear exactly where these are launched from. So we can use the NUV excess above the stellar photosphere to extract an accretion luminosity and use this to measure the mass accretion rate onto the star using accretion shock models. So on the left is a schematic of the model I'll be using in this talk to measure accretion rates when you hear me talking about accretion rates later on. And in this model, it's assumed that the shock is plane parallel, which is justified by the small extent, and that the emitting region is a vertical column that's constrained by the magnetic field. On the right is an example of using this model to fit data. So the gray is the data of a T-Tauri star and UV and optical of BP tau. The blue here is the emission from a template stellar photosphere. So this is actually a weak T-Tauri star, which is a T-Tauri star that is not accreting. The total model, which is in red here, combines the stellar photosphere, the heated photosphere, and the pre-shock, so 2 of the model components. And from that, we can extract an accretion rate. So the accretion process is observed to be variable. And there are many, many studies on this. But since here I'm focusing on the NUV, I just have this one slide to show. Here are multi-epoch HST FUV through near-infrared observations of 5 T-Tauri stars. And this is the largest NUV variability study so far. In the gray, I've highlighted the NUV. And if you look closely for each of the objects, you can see the continuum never really matches. So every time we observe these stars, the accretion rate's a bit different. And all of these changes in the NUV continuum are due to the variability of accretion on the surface of the star, since that's what's dominating the NUV emission. Okay, so that was a very quick intro into accretion and T-Tauri stars in the NUV. And now on to the second question. So what do we learn from simultaneous multi-wavelength data? And we'll be approaching this question. So how do we learn about the star-disk jet connection using the variable accretion of the NUV to anchor us and then comparing it to the different wavelengths, what we're seeing there. Okay, so to overview the program, for one target, we obtained 3 epochs of data for 1 T-Tauri star separated by about 1 week. And we got data with Chandra, HST, Spitzer, and the VLA. The observations were strictly simultaneous, so they overlapped. Maybe they didn't overlap by 5 or 10 minutes, but for most of the observations, they overlapped. So this was the first simultaneous observation of a T-Tauri star at this broad wavelength coverage. So the X-ray emission is tracing the emission from the star. In the UV, we got NUV and FUV data with HST. The NUV traces accretion, and the FUV, which I'll show you later, traces gas in the innermost disk. With Spitzer, we got infrared, which traces the dust in the innermost disk. And with the VLA in the centimeter, that's tracing the emission from the jet. So it's hard to do this test of trying to see what's the connection between the star, the disk, and the jet for the objects that have the strongest jets, because they're actually the objects, they're more embedded, and it's nearly impossible to observe the UV for those objects due to extinction. So there are a handful of disks, protoplanetary disks, that are not heavily embedded, but still have jets, weaker, but still detectable. And the object that we chose for this study was the T-Tauri star Geomorrhagi. So we chose this object for many reasons. First, it's a low mass star. So for low mass stars, we understand the accretion mechanism. For the brighter, more massive, easier to observe Herbig AEBE stars, we still aren't completely sure about how accretion proceeds in those systems. Geomorrhagi is also a transitional disk. So here's a millimeter image, model, residuals, but in the millimeter image, we see evidence that there's a hole in the disk. In particular, a radius, this hole has a radius of 20 AU. And we like that because we don't want to deal from obscuration of dust in the inner disk, causing variability. Geomorrhagi also has a known jet detecting the centimeter emission. So in the centimeter, you see emission from the photoionized disk and also a jet perpendicular to it. This object is also known to have variable NUV emission. So we wanted something where we knew from previous observations, it was variable in NUV. Here in the NUV, you see the stellar photosphere. These are 2 different epochs with HST data. So there is NUV variability in this object. And also, Geomorrhagi has a little bit of near-infrared excess. So here we have the stellar photosphere, and there's a little bit of near-infrared emission above the stellar photosphere. And that's good because even though there's a big hole in the disk of 20 AU, there's still a little bit of dust close to the star. And so we can use this near-infrared emission for this object to trace the innermost edge of the disk. And then lastly, this object has been detected before in the X-ray. So we know we could get enough photons for this one. Okay, so now I'll step you through the measurements that we made of the mass accretion rate, the dust and the gas in the innermost disk, and the mass loss via the jet. And I'll come back at the end because it's a lot of data and wrap it all up. First, what accretion rate do we measure? Okay, so here we have all the HST data of Geomorrhagi compiled before our observations and including our observations. And we were very lucky that Geomorrhagi was caught during an accretion burst in one of our simultaneous, one of the epochs of our simultaneous wavelength campaign. So here we have again HST data, NUV, optical, near infrared, 8 epochs of Geomorrhagi. Here I'm only going to focus on the last 3 epochs, epochs 6, 7, and 8. Those are the 3 epochs where we got the simultaneous X-ray through radio data. And I'll be referring to them throughout the rest of the presentation as the first, middle, and last epochs of the simultaneous campaign. So you can see if you look in the NUV, when it was bright, when Geomorrhagi was brightest in the NUV, it was actually epoch 7. So we were very lucky. So let me step you through the 3 HST spectra that overlap with our simultaneous data set. The first, here in yellow, epoch 6, we measure an accretion rate of 0.6 times 10 to the -8 solar masses per year. For reference, a typical T-Tauri star accretion rate is 1 times 10 to the -8 solar masses per year. A week later, the accretion rate went up by a factor of about 3 to the highest observed NUV state of this object. And then a week later, the accretion rate went back down to about 1 times 10 to the -8 solar masses per year. So going forward, I'll be showing you the data at the other wavelengths, focusing on these 3 epochs. And I just want you to keep in mind in the middle epoch, we had the accretion burst because we're going to keep coming back to that and tying things to that. Okay, so what are the dust and the gas in the inner disk doing? So here are Spitzer data for the 3 epochs. For each epoch, we got 2 bands at 3.6 and 4.5 microns. This is tracing the infrared excess that I showed before that's coming from dust within an AU or so of the star. In the middle epoch, the infrared emission was highest. And if you remember, there's an accretion burst in the middle epoch traced by HST. So, what's interesting is that the flux in the first and the last epoch are consistent with previous observations with Spitzer, where we had already modeled how much dust was in the inner disk based on this flux. And if we use the same models, we get that we can explain this increase in the infrared flux with a factor of 3 change in the dust mass between epoch 6 and 7. So we're concluding that this increase in flux in the mid-infrared is due to an increase in the surface density in the inner disk, and therefore that propagates to the mass that is accreted onto the star, and we get a higher accretion rate. So what about the gas in the inner disk? So for our observations, we also obtained FUV HST data in addition to the NUV data. So there's a feature in the NUV called, the FUV called the H2 bump. The H2 bump is this little thing here. It's between the very strong carbon-4 and helium-2 lines. This feature is a combination of H2 emission lines and broad H2 continuum emission. And it's seen in several accreting T-Tauri stars. And it's been found to trace gas in the inner AU of the disk. So if we zoom in, we see that in the middle epoch, the H2 feature is at its highest, and the flux is actually a factor of 2 higher, which is roughly consistent with the factor of 3 change in the accretion rate and the factor of 2.5 change in the dust mass in the inner disk, again supporting that the surface density in the inner disk is increasing. So we seem to have a connection between the star and the disk. What is the jet doing in the VLA observations? So the centimeter emission also appears to increase as the accretion rate increases. Here, the centimeter observations are the circles, the squares are just the accretion rate. So in the middle epoch, the centimeter emission is the highest. Now, and this is consistent with the well-known relationship between the mass loss rate and the mass accretion rate. Now, because of the VLA configuration schedule, our data were low resolution. So we can't disentangle the jet emission from the photoionized disk emission. But it's very likely that the 3 centimeter emission is tracing changes in the jet and not the photoionized disk emission. And that's because we got the simultaneous X-ray data and it did not change at all. And this is important because if the X-ray isn't variable, then we don't expect changes to be from the photoionized disk, since the X-ray is what's dominating the photoionization of the disk. And since X-ray isn't changing, it also rules out that the X-ray is responsible for changes in the FUV, NUV, or mid-infrared. Okay, so let's tie this all together. So what we think is happening is that the surface density in the inner disk is increasing. So this is not a global change that would not be consistent with the viscous timescale, but maybe there's some inhomogeneity in the inner disk, something like a clump. And we see this as an increase.
2-minute warning.
Okay, thanks. And we see this as an increase in the mid-infrared emission and also the FUV emission. So as the surface density in the inner disk increases, the mass accretion rate increases, perhaps as the magnetic field line goes through the clump. That leads to more matter being dumped onto the star, and we see that as more NUV emission. And then if there's an increase in the mass accretion rate, there would be an increase in the mass loss rate because of that well-known correlation. A caveat here is that we wouldn't expect the jet emission to increase simultaneously with the accretion rate because it takes time for that material to travel. So instead, it's likely that we're seeing a minimum and maximum to the accretion rate and a minimum maximum to the jet emission. And that maybe this change that we're seeing in the jet emission is coming from another accretion burst that we missed that happened a few days before. So what is presumably connecting the star, the disk, and the jet? So we would think that's the magnetic field, which has been shown, which is thought to lead to material channeling onto the star and also eject it from the system via collimated jets. So here we're concluding that we're seeing the star disk jet connection. And this was a pilot study. And my group and I, we have a follow-up study, and hopefully we'll have results on that by the end of the year. So then very quickly, where do we go from here? There's going to be a lot of work in the near future on accretion variability with HST. So we're going to hear later on in this session from Will Fisher about a very big UV legacy program called ULLYSES. Half of that time will be dedicated to T-Tauri stars, and Giamaraghi will be one of them. And I just want to quickly highlight that the community has gotten together to analyze and work with this ULLYSES program data from HST. And we formed a community called ODYSSEUS with over 50 young star experts from around the world. And we'll be working together collaboratively on the ULLYSES data set from HST, and we'll be working to further understand accretion, winds and jets, and the impact of FUV radiation on disk chemistry. And here's just a big list of complementary data that we are acquiring within the team to supplement the HST ULLYSSES data, ranging from the X-ray to the near-infrared wavelengths. So stay tuned for results coming out in the next few months. All right, so I'll just leave up my 3 main takeaways and I'll take any questions. Thank you very much.
Okay, we're gonna have to get used to it.
That's really nice. I haven't had clapping before. Nice.
So just a reminder to ask questions, please use the raised hand emoji and turn on your video to ask the question, and we'll go from there. Okay, I see Zafar has a question.
Hi, that was a really cool talk. I was really curious to know what the spectral structure in the MUV tells you about the star and the material potentially of the inner disk.
So the NUV emission lines? Yeah, so we do find that the NUV emission lines correlate with the mass accretion rate. So there are some well-known correlations for the different lines we see in the NUV. Right now, we haven't really been able to successfully model the NUV lines or the FUV lines with the accretion shock model. And that's something that we're doing as part of the ODYSSEUS collaboration. So right now we've been able to fit the NUV continuum, but can we fit the NUV lines and the FUV lines? But there are correlations with the accretion rate. We just can't reproduce them with models just yet.
James Jackman is up next.
Hello. Previous studies, I believe, have suggested that flares from the main star can trigger accretion events from the disk. Were you able to detect any kind of flare-like events occurring before the increased accretion or not?
So our data were simultaneous, so we don't have information before or after. So I showed those 8 epochs of HST. For one of the previous epochs, we did have X-ray monitoring data, and we did see that there was an X-ray flare in G with a higher state of accretion, not as high as what we saw here, but it was higher. And so we did speculate in that paper that maybe there's a connection there between the X-ray flare and the accretion rate increasing. So we did see that once, but we haven't been able to catch it happening again.
Cheers.
James.
Hi, Catherine. So I was wondering, is the near-infrared Spitzer excess and the H2 bump, are they optically thin or are they optically thick? Or I guess what do the models suggest they are?
Yeah, thanks for bringing that up. Yeah, so it's important. We're assuming that they're optically thin. This is usually the assumption that's taken for the dust. We've done different studies. We've tested if it's optically thick or optically thin. It's consistent with being optically thin. With the FUV feature, it's typically assumed that it's optically thin, and we don't have any reason right now to think it's optically thick. So yeah, right now we're assuming both are optically thin, and so that we can use that as a tracer of the surface density. If it's optically thick, then the story changes.
Okay, we have time for one more question from Ruth.
Hi, Catherine. What's the area over which that density is changing, like in the inner disk?
Yeah. So in the model, when I'm modeling that change, I guess you're asking for the mid-infrared. In the model, it's about an AU or so. But in our model, we can't have inhomogeneities. It's all like radially homogeneous. So yeah, so basically we're assuming it's over 1 AU, but then we're interpreting it as it would be coming from within a clump because it's not consistent with the viscous timescale that you would have, matter dumping in within 1 AU and then that gets to the star.
What was the timescale again?
So the change is at a week, but we don't have finer sampling than a week.
Thank you.
Great, thank you. Any additional questions, please direct them to the chat and they might be able to be answered there. Otherwise, take it to GatherTown and some great discussion can be had. Next up, we have Christian Schneider. Christian, are you here?
Yes, I am.
Oh, great, awesome.
It's just trying to share my slides.
No worries.
Yeah. That should do it. Okay.
Great, thank you.
Hello, everybody. My name is Christian Schneider from the Hamburg Observatory, and I'm going to talk about extended UV emission in young accreting stars. So to briefly remind you about the stage of the star formation process, where the objects are, about which I'm going to talk about, and about which Catherine talked about. So that is that intermediate stage between the initial collapse and the final product. So we have a disk, we have jets, we have accretion, and all that is seen in the UV. And I think that probably most people would agree that the hot ion lines, so lines that are 10,000 Kelvin or so, should come from accretion, because we need the kinetic energy to heat the material, and it's really the accretion shock, or the region above the, immediately above the accretion shock, where we have these hot ion lines. And additionally, we have the correlation between, for example, the carbon-4 line or doublet and accretion luminosity or accretion rate. Here, the x-axis, you have the carbon-4 luminosity, and on the y-axis, the accretion luminosity or accretion rate, and they do correlate over 3 to 4 orders of magnitude. So most people will probably think of carbon-4 emission as an accretion tracer. And we want to check that. We want to see if that carbon-4 emission really comes from accretion, or if this has other contributions. So what we did is we tried to spatially resolve the carbon-4 emission, and that is what we did. We placed a long slit with the Hubble Space Telescope along the jet axis, so we get distance information and a spectrum at each point along the slit or along the jet. So that means we get a position velocity diagram, and I will show you 2 examples for dg tau and SZ1, 2. And these are the 2 position velocity diagrams. You have the x-axis, it's velocity on both panels, and the y-axis, it's distance from the star. And the star is obviously at 0. And I want to stress that I added both doublet lines, and I removed the H2 emission, the contaminating H2 emission, but I did not remove any emission from the star. So what we see here is that there's no emission from the stellar position. There's only emission that is offset from the star. And it's on the left, it's shifted to high velocities, but on the right, if you do not have spatial resolution, and you would just collapse the spectrum, then you will get the spectrum that you see on the left side, and it's almost peaked at 0 velocity. So that's exactly what you would see in all other accreting stars. Carbon-4 emission centered at approximately 0 velocity, broad emission, and that looks like accretion, but in fact we know from the right panel that it's not coming from the star, it's actually coming from the jet, what we see here. And how does that? We know that jets are variable, and we did obtain a second epoch of both objects for SZ102 because of the malfunction of HST. We got a chance to take a second epoch. On the left, that was intentional, and we see that part of the emission is actually moving away from the star along the jet direction. That may happen here in SZ102, but most of the emission is actually stationary. It's in both epochs, it's close to the star, and the red contours are the highest contours from the previous epoch. So that is, the emission remains close to the star, and also its spectral characteristics remain almost constant. So that means also for the right part, it would again look like accretion also in the second epoch data. So that's very interesting. So we have emission that looks like accretion, but it's actually from the jet. So maybe do we have additional indications that part of the hot ion lines come from the jet or from extended emission and not from the star itself? Well, yes, we have. This is the light curve, the optical light curve of AA tau. And you see that in 2013, 13, the object got much dimmer, so 3 to 4 orders magnitudes, or 3 magnitudes dimmer than before. And we were lucky. There's one cos epoch before the dimming and one cos epoch after the dimming. And if you look at the continuum emission, this is the spectrum, or these are the continuum data points before and after the dimming. On the top panel is the actual flux, and on the bottom panel is the ratio. If you remember, the object got dimmer by 3 magnitudes. That's more than a factor of 10. And what you see here is the ratio, and that is maybe a factor of 2 or so. Then I've also overplotted the blue and red line wings of the hot ion lines. You see that the red line wing actually decreases almost as strongly as the optical, but the blue line wing stays constant or reduces only little, and in fact less than the optical brightness. And it's impossible to get that with any extinction law in the universe. So that emission cannot be subject to the same extinction as the star or the immediate region around the star. So if we then go back and look at the correlation between carbon-4 and accretion, then we have again on the x-axis the carbon-4 luminosity, and on the y-axis accretion rate. And the green dots are the 3 examples that I've shown you, where I assumed the extinction towards the star, the measured extinction towards the star, and use that to de-redden the observed fluxes. So this is what you would do if you would not know that it comes from the jet. And so that brings me to my conclusions. There is significant carbon-4 emission and probably all other hot ion lines from jets, or maybe from extended structures, maybe scattering and other objects too. You would not see that from the fluxes when you de-redden the fluxes with the stellar AV. Even the spectrum, in some cases you may see the blue shift, but in other cases the emission is centered at 0 velocity if you have no spatial information. And what I have not shown you is that it's a great tool for jet studies. Actually, it gives us information on the launching and the heating of jets, and actually the stationary nature makes it possible to connect that back to the disk magnetic field. But that shall be it. So the important message is that carbon-4 emission, what typically associated with accretion, can come from jets. Thank you.
We'll get in the habit of it. We will.
Christian, I had a question. Would this be a tool to potentially also study jets from, say, accreting planets around young stars?
So the important reason why we get this carbon-4 emission is that the jets are very high velocity. And from planets, you would probably not get those high velocity jets. So you would need 100 kilometers per second or so jets.
Thank you.
But they do drive, or there are models that show that accreting planets drive jets too.
Awesome, thanks. Kevin France.
Hi, Christian.
Kevin.
Ask about how universal this result is. DG Tau and SZ102 are pretty strong optical jet sources as well. For an average T-Tauri star that doesn't show strong optical jet emission, would we expect carbon-4 to more carbon-4 coming from on-star versus off-star, or how universal is this conclusion?
That depends actually on how strongly the stellar or the accretion carbon-4 is extinguished by the luminosity from the accretion is higher, but also the extinction to the accretion is higher, or to the accretion generated carbon-4 emission is higher. So that really depends. I mean, for AA tau, we had seen that a significant fraction is in the blue line wing, and that is not accretion generated.
Thank you, Christian. We must move on to our next speaker, which is Nicole Arulanantham. Nicole, are you present?
Yeah, I'm here. I'll share my screen before putting it in presenter mode. Let's see. Okay, can you see it?
Yes, I see your screen and it is awesome.
Full screen? Okay, perfect. So that was actually a really great pronunciation of my last name. Thanks, Lauren. I'm actually now a postdoc at Space Telescope, and I'm really excited to tell you about this paper that was recently submitted where we investigated how UV fluorescence actually traces this sequence of gas and Lyman alpha evolution in protoplanetary disks. And this figure on my title slide kind of shows the main meat of what that sequence is. So we'll come back to this at the end of the talk, but I just wanted to give you a sneak preview. Now, I wanted to set the stage for this project by first showing you 3 images of the disk around TW Haya at submillimeter wavelengths. So on the left-hand side here, we're looking at continuum emission from cold dust in this protoplanetary disk. And we can see this nice centrally peaked distribution of dust that tapers off as we move to larger radii. And this is a fairly low spatial resolution image. We would see much more substructure in this dust in images at higher resolution. So we have a pretty good sense of what the dust is doing during planet formation. But when we look at the molecular gas, which will tell us a little bit about the initial conditions for planetary atmospheres, we sometimes see something very different. And what we see seems to depend on the molecular species that we're looking at. So in the middle panel here, we're looking at CO emission from TW Haya. And again, we see this nice centrally peaked distribution. But when we look at molecules like N2H+, for example, we see something very different. So instead of a central peak, we see a hole in the middle and then a bright ring of emission. And this is something that's seen in other molecules as well. So for example, CN, C2H, and I think even H2CO. So these are molecules that are carrying important volatile elements. And it turns out that this ring-shaped emission can be very naturally produced as a consequence of chemical formation pathways that depend on the UV radiation field. So we really want to characterize the UV radiation fields from these T-Tauri stars in order to understand the physical distribution of planet-forming gas in these disks. Now, my favorite way to investigate this connection between the UV radiation fields and the molecular gas disk is by looking at UV spectra of H2 and CO emission. And these features are produced when Lyman alpha photons pump the molecules into excited electronic states, and then we see a whole cascade of emission lines as the molecules return to the ground state. So in both of the panels on this slide, we're looking at an example of what those spectra might look like. And we can see that the H2 emission follows this nice clean pattern. We see this nice spectrally resolved emission line. And this makes it relatively easy to extract some information about the radial distribution of gas that produces this emission line. But because CO is a heteronuclear molecule, it has a lot more allowed transitions. And so instead of a nice clean emission line, we see this mess on the right-hand side. So each of these blue lines here marks off a lab wavelength of a CO transition. And we can see this big pileup of states at the band head. And when we zoom in on the longer wavelength region of the spectrum, we can see that we still have a lot of blends producing all of this flux. So it's much harder to extract radial information, and we wanted to fit 2D radiative transfer models to the CO bands in order to back out some information about the spatial distribution of emitting gas in that way. And it turns out that this is also much, much harder to do for CO than it is for H2. So here we're looking at an example of a CO band from the disk around AA tau. So the data here is shown in black and our best fit model is shown in teal. And I put a frowny face here to remind us that this is not a good fit at all. And if we come down to this bottom panel here, I've color coded the residuals based on the pumping wavelength of Lyman alpha required to excite the upper wavelength or the upper level of these transitions. And so we can see that the models do the worst job in regions where we require some central source of Lyman alpha to excite the upper levels, and where we need some redshifted source of Lyman alpha to pump the upper levels. Now, we know that AA tau is a pretty weird system, and I've shown this figure here mainly for dramatic effect. But it turns out that even with disks that have much better best fit models, we're still missing some of this red Lyman alpha. So clearly we're missing at least one, if not multiple sources of Lyman alpha emission in our models. And so the question now becomes, how can we account for these missing sources of radiation in order to get a better sense of how the gas is physically distributed in the inner disk? And it turns out that the observed Lyman alpha profiles actually provide more information than we originally thought they did. So, oh, thanks. In the upper left corner here, I'm showing a Lyman alpha profile from the young system UX tau. And we have the middle lost to interstellar absorption and geocoronal emission. But if I divide this profile into two sections and calculate the red and the blue Lyman alpha flux, and I do the same thing for the CO, where I add up all the band head emission and all of the emission from higher energy transitions, when I plot these two quantities, we see this really nice, strong linear relationship. So this is telling us that actually the Lyman alpha profile that we observe here is very reflective of what the molecular gas is actually seeing in the disk. So this becomes a really nice place to start. And when we combine these Lyman alpha flux ratios with all of the other information we have about these disks, we see that the sequence of evolution kind of very naturally falls out. So in the upper third of this plot, we have targets with outflow dominated Lyman alpha profiles. So these are systems with more red than blue Lyman alpha flux. All of the disks in this group have very strong signatures of jet and outflow emission, and their dust disks are less evolved than the systems in the bottom third of this plot, which have more blue Lyman alpha than red flux. And these are all targets with much more depleted dust distributions, which may tell us that these are in the later stages of disk dispersal. And any material that's rapidly draining onto the central star could be responsible for suppressing the red side of the Lyman alpha profile. And then we have a whole clump of targets that fall in the middle of our plots, and I can talk more about these later if anybody is interested. So I'll leave you with some of the questions that I'm most looking forward to answering. This is a very interesting result, but we still have a lot of work to do. So we'll be investigating whether these trends hold when the sample size increases. Of course, this was just a very small sample of 12 disks. We also want to investigate whether similar categories are seen when we include other Lyman alpha sensitive molecules. And finally, we want to see whether other accreting systems with similar reversals in the Lyman alpha profiles can provide some insight into what's happening in these disks. So that's everything that I wanted to show you, and I'm happy to take any questions.
Thank you.
James has a question.
Hi, this is very, very interesting. So are the disks with the depleted dust cavities, are these sort of the classic transition disks that have whopping holes and they're still rapidly accreting, or are these more some of the sort of low disk mass, low accreting small hole transition disks?
So these are the disks with massive holes. So these are systems where the inner disk regions are completely depleted. There is still ongoing accretion. So actually, when we compare the Lyman alpha flux ratios to the UV derived accretion rates, there's actually no significant correlation. So these trends appear to be independent of the accretion rate.
I see in the chat, Lynn Hillenbrand is asking, the last figure, last figure was a beautiful demo. Thank you for that.
Thank you.
Okay, we have a question from Ruth.
Hi, that was so interesting. I'm trying to figure out exactly what I should ask, but in your diagram at the end, you have the H2 and then the CO and then the dust. And is that from, maybe you said, but is that from shielding? Why is the H2 extending further in than the CO?
Yes, that's a good question because I actually didn't say. So these are placed here. So yes, shielding is the short answer. It seems like the column densities of H2 are able to build up in more further away from the edge of the dust rim than the CO. I will say the locations of these emitting regions, of course, should be taken with a grain of salt because since we don't fully know how to characterize the Lyman alpha radiation field, it becomes very difficult to figure out where exactly the gas is coming from. But yes, shielding does seem to make it easier for UVH2 to build up to an appreciable column density further away from the edge of the dust rim than the CO.
Great, thank you. Up next, we have Laura Flagg.
Oh. Hi, I better start my video. Hi everyone, I'm going to be talking about molecular hydrogen detection, and I'm going to move on a little in time from Nicole's talk and to debris disk systems and what we can learn about the H2 in those systems. So, as Nicole mentioned and described very well, most of what we know about planet formation comes from what we learn about dust, because dust is stupidly easy to detect, especially in comparison with the gas. But gas is most of the mass, at least in the protoplanetary disk, and even in debris disk systems, still has an enormous impact if you care about things like disk dynamics or your planet having an atmosphere. And in particular, warm gas, because warm gas is what is in the terrestrial planet forming region, is very hard to detect. You can detect cooler gas and with radio or far observations, but H2, which is most of the gas, only has allowed transitions in the UV because it lacks a dipole. And so we look in the UV to detect H2 fluorescence transitions, generally pumped by Lyman alpha. Since we understand the dust relatively well, we wanted to compare what we know about warm dust with warm gas. So we looked at objects in upper SCO, about 10 million years old, that don't have warm dust, to see if we can detect warm gas in any of them, to determine how the dispersal timescales may vary between those gas and dust. And unlike in protoplanetary disks, where the H2 lines are generally very obvious and you can detect them by eye, these H2 lines would likely be very weak, so we use a cross-correlation function to boost the signal. But before I started on the upper SCO objects, I am a responsible scientist, so I tested my code on TWA7. I used TWA7 because it is about the same age and it had a COS observation with null detection already. However, instead of a null detection, I got a detection, and after many iterations of checking my code to make sure it wasn't a false positive, we get this final result, a 5+ sigma detection of H2 in TWA7. Very clear detection, despite several previous null detections. The problem is that M dwarfs like TWA7 have H2 in both their photospheres and their star spots. And we want to be able to distinguish between a stellar origin and a circumstellar origin. And it turns out this is very tricky, especially for systems like TWA7, which are very face on. For TWA7, what we did was we looked at the line ratios. Since it's for COS observations, it's hard to look at Lyman alpha directly. We look at which H2 lines are the strongest as a way of basically back tracing the Lyman alpha. And broader Lyman alphas are typically indicative of accretion. And TWA7's line ratios from the cross correlation function are very similar to those from classical T-Tauri stars and very dissimilar to those from M-dwarf main sequence stars. So we concluded that the H2 in TWA7 is very likely to be circumstellar. All right, now on to our sample and upper SCO. So we have detections in 10 of the 26 observations, despite no near-infrared dust in any of these. Of those 10, we're very, very confident in at least 3 of them, including this one. This is a K1 star. So, but again, we have the problem, star disk. We have different spectral types here, so it's less likely to be in the photosphere, but star spot is still a potential origin. You should note that we have, between our confirmed detections, there is a slight correlation with W4 excess. But mainly, we don't see a correlation with spectral type. And if the H2 is from the star, we would expect to see a correlation with spectral type. So our conclusion that the H2, especially in these earlier type stars, is very likely to be circumstellar.
2 minutes.
And so we're consistently seeing warm H2 without warm dust. All right, skipping ahead a little time, since this gas outlasts the dust, how long does it last? We looked at AU-MIC, which is about 10 million years older, confirmed the detection initially discovered by France et al. 2007 with some data from 1998 and also 2020. And initially, we got the same conclusion that it was circumstellar because the temperatures we measure are fairly cold, about 1,000 to 2,000 Kelvin, and the star just models indicate and measurements indicate it doesn't get that cold. Even the star spots only go down to 2650. However, this line profile shown in blue is from a flare is very similar to that in quiescence. And if the H2 was in a disk, we'd only see a very narrow profile because only a small portion of the disk with only a small portion of the velocity of dispersion would be illuminated by the flare. And so this is inconsistent with the circumstellar origin. Also, AU-MIC has a planet too, and it's not in the planet because we know approximately where the planet is in RV space, and the H2 does not trace that. It basically scatters around the systemic RV. So by process of elimination, it must be from the star, despite the temperature being unexpected. This hints at unexplored physics and stellar structure. AU-MIC has a really complex magnetic field, so perhaps that contributes. Colder region of the photosphere. The sun has this thing called the ceomosphere between the photosphere and the chromosphere. It wouldn't be called the ceomosphere because AU-MIC is colder, but something like that. In conclusion, we are very, very good at detecting H2. Our methods increase sensitivity by a factor of 10, but determining origin is more complex. And we have significant evidence that warm gas lasts longer than warm dust, but we don't know by how much. And with that, I will take any questions.
Thanks, Laura. Questions from the audience? All right, so I see in order on my screen, James Owen is first, and then we'll go to James Jackman.
Hi, Laura. Very cool results. I may have missed this, but sort of, do you know what radial scales you're probing with this this warm gas?
Yeah, so we
Could
generally
it be tens
think
of AU from the star, I guess, is my question.
unlikely. It's very, very unlikely to be tens of AU. So models generally have not been run, but you need to get up to about 1,000 degrees, and it's very hard to get that warm at tens of AU. We're probably talking at most 5, 6 AU, and even then it's iffy, but not tens of AU.
All right, James Jackman, you're next.
This is probably something I've missed or forgotten, but you mentioned if the H2 were from the stars, you'd expect a correlation with spectral type. Could you briefly explain why that is, why you'd expect such a correlation?
Right, so H2 starts dissociating into atomic hydrogen between about 2000 and 4000 Kelvin. And so the warmer the star is, the less H2 we're going to see. And obviously there are, because it would, in this point, it would be in this, the star spot, and star spot temperature doesn't perfectly correlate with photospheric temperature, but we would think we would see some correlation, and we see nothing. Yeah.
Great. In the interest of staying on time, we should move on to our next speaker. Again, questions in the chat is totally fine at this point. Up next, we have Will Fisher.
Hi, you should be able to see my screen now.
Yes.
So I'm going to tell you all about ULLYSSES. It's a Hubble program that's producing a lot of data for community use. This is the Ultraviolet Legacy Library of Young Stars as Essential Standards. And plans for this started coming together in 2018, 2019. It was recommended by a working group made up of mostly of external scientists. It's modeled like the Frontier Fields program. It's all director's discretionary time. And it consists of 1,000 orbits being observed between 2020 and 2022. Half of those are for massive stars. The other half are for T-Tauri stars, and that's what I'm going to focus on here. The data become publicly available immediately, and STSCI staff are selecting targets, implementing the observations, and creating data products. So this is how the selection of the T-Tauri stars works. The working group asked us to sample a broad range of spectral type, age, and disk accretion rate. The plot here shows accretion rate versus stellar mass for the stars in the sample. The star symbols are archival targets that have already been observed, and then the circles are new ones that we're going after. They asked us to include about 40 T-Tauri stars in the survey. We actually have plans for 61 at this point. It was adjusted recently from 67. If you've been following this closely, there's some explanations on the slide as to why. And we're really emphasizing southern star forming regions that aren't well represented in the archive already: Lupus, Chameleon 1, and a few other smaller regions. In addition to the survey sample, we also have a monitoring sample. These are 4 prototypical bright T-Tauri stars that we're going after: BP Tau, GMOR, TW Haya, and RU Loop. And I'm mentioning our website over and over again on my slides, but you can go to ulysses.stsci.edu and see target tables, including observation dates. The observing strategy for the T-Tauri stars. So this shows archival spectra of GM Aurigae, some of which you saw already in Catherine's talk, but this just illustrates the wavelength coverage and resolution that we're getting for the stars in our survey sample. COS is observing the FUV at medium resolution, and then we're getting STIS low resolution data through the NUV and optical. And our signal to noise goals are shown there. For the monitoring stars, we're getting more limited wavelength coverage so that we can fit all the observations into single orbits. We're just getting the sort of longer wavelength half of the COS range, the COS M range, and then some data around the magnesium line with COS G230L. So far, we have observed 13 T-Tauri stars in Orion last fall. That image shows where they're distributed on the sky, and then I have the spectra of one of them, CVSO 107. These were coordinated with TESS observations, LCO-GT photometry, spectroscopy with VLT and IRTF, and lots of other ground-based photometry. And we grouped the STIS and accompanying cost visits to a given target within 1 day. One of the results that came out of this was we discovered a couple of companions to 2 of the T-Tauri stars. The companion to CVSO 165 is also a T-Tauri star. The companion to CVSO 109 does not appear to be accreting. And we have a research notice of the AAS that allows the community to cite this that we put out. The first results from the time monitoring campaign are in for TW Hydri. We observed it 4 times per period over 3 rotation periods. That's the general tactic for these stars in late March, early April. The first visit was off-center in the aperture a little bit, but we can fix that. The 9th visit failed altogether, but most of the visits resulted in good data. You can see the carbon-4 and magnesium-2 lines here. This was a little tricky. HST went into a pretty significant safe mode less than 48 hours before we were scheduled to start. So we had to sort of work frantically with schedulers from Chandra and other observers to try to recover all the coordinations. We did pretty well with that, but we lost part of the tests overlap because we weren't able to get it back onto the schedule until the end of March. We're also doing at the Institute, we're coordinating the photometric monitoring with LCOGT. This is V and I band photometry for the survey stars, plus U for the bright monitoring stars. And you can see here an example of what we're getting again for CVSO 107. We have observations 90 days before, 90 days after, and then from T minus 10 days to T plus 10 days with finely sampled observations every 15 minutes during the actual HST observations. So this puts everything in context. And I wanted to mention one element of the plan is to cover a full rotation period that encompasses the HST observations. You need to know the rotation periods to do that. So Javier Serna at UNAM has been really instrumental in providing estimates of the rotation periods from test data. We also have a lot of other community-led coordinated observations going on. Catherine mentioned a lot of these. A lot of the programs are named after Ulysses' friends and relatives from his story in Greek mythology. And then there's the big ODYSSEUS archival research program that Catherine mentioned. As far as how things are going now, survey stars in Chameleon and Lupus are being observed between test sectors 37 and 39. Right now, Hubble is pointed at SZ75 to get cost spectra over the next few hours. The first epochs of the remaining 3 monitoring stars are coming up in August through October. We'll get back to their second epochs 1 year after the first. And we'll pick up again with survey stars in Chameleon and Lupus next spring. There are lots of data releases about every 6 months or so being put out that are giving the community products beyond what normally just appears in the Hubble archive. First data release was mostly focused on massive stars. The second data release in March had high-level science products for our Orion targets, custom calibrated STIS spectra of the companions that we discovered, and additional files for aid in kind of reproducing those reductions. The third data release is scheduled for August, and it'll have our monitoring data for TW Hydri, high-level science products for the Lupus and Chameleon stars we're observing now, and the LCOGT data, and then additional data releases every 6 months or so after that. This is your Ulysses core implementation team at STSCI, working on all sorts of aspects of data products and the implementation of the observations. So there are about 24 of us there. And additional thanks go to our program coordinator at Space Telescope, the schedulers, the archives division, public outreach, and our external science advisory committee. The first 4 people listed there are the T-Tauri star experts, at least 2 of which are online with us today. So I'd like to thank everybody who's contributed to this so far, and hopefully everybody can make good use of the data we're putting out. Thanks.
You. Questions for Will? Well, I was wondering if you had an estimate of the number or like the distribution of stars with disks compared to stars without disks in the sample.
There are we've tried our best to make sure they all have disks and are accreting. There are a couple that haven't slipped in, and then we've intentionally added a couple of weak line T-Tauri stars for use as templates. But our sample selection was designed to include stars with disks.
Thank you. Zafar.
Hi, that was cool. So the one disk that had a companion, the one T-Tauri star that had a companion T-Tauri star, do you know how far apart they are? Do you know if they're interacting? And do you think that'd be interesting to follow up on with ALMA, for example?
Yeah, I encourage you to write an ALMA proposal if that interests you. I think the separation was, these are in Orion, so maybe 400 parsecs, and it was a few tenths of an arc second. So you can work out the physical separation from there.
Thank you.
Okay, thank you, Will. Again, any further questions can be added to the chat. We have one more speaker for this session. This is Gerard Van Bell.
Thanks, Lauren, and thanks, Evgenia, for the invitation. I'm delighted to be talking today about a mission opportunity that we are thinking about putting together for proposal for this upcoming MidX mission opportunity call. This is a observatory we're calling LightBeam. And basically the idea here is milliarc second imaging inside of a small sat package. So we will have basically a optical interferometer. We want to fly in space, be the first long baseline optical interferometer in space with a 20-meter baseline, and it would go down through the visible into the beachhead of the near UV down to about 2,500 angstroms. Basically get to the point where detectors aren't terribly difficult to work with. The important thing here is having an interferometer in space, you don't have to deal with the Earth's atmosphere. And so you actually pick up a great deal of sensitivity. We have very small apertures on board, 2-inch apertures basically on each of these outboard optical units. But we get down to about 17th magnitude because we are able to not be limited by the Earth's coherence time. The way we get a big thing into a small package is we start off very small. You basically fly something that's compatible with a ESPA class small sat. ESPA class means you fit into about 1 meter cubed and you weigh about 200 kilograms on the outside. And then you print these booms. You actually have 3D printers on board that print the booms that hold the outboard optics. Why do you do 3D printing in space? Well, you get a great deal of weight savings. The booms can be quite a bit more gossamer. They don't have to survive launch. And you get quite a bit of volume savings there as well. You don't have any kind of complex origami to deploy things. You just print this stuff out. Now, I know that this sounds to many of you very pie in the sky, but the simple fact is that many of these units are already flying. This technology and this mission concept has been pursued by Lowell Observatory and then also my partners over at Maiden Space. And the print on this slide is kind of fine because it details all of the printers and other manufacturing units they have on board the ISS. We have a specific unit called ESAM that would be for this mission, and it's been thermal vac tested. It's already demonstrated the world's longest 3D print. They ran out of optical shop space when they were trying to run this, and so they had to terminate the test at 37 meters. And the company also has a flight mission already selected for flight where they're going to print the support structures for solar panels that'll fly as early as next year. For demonstrating this, the Maiden Space and Lowell have a NASA SBIR grant. This was over the course of this past year where part of that I built up a prototype optical beam combiner that demonstrates basically the optical package for this flight mission. And the idea was to build it in the lab, but then COVID hit. So I built this in my kids' playroom on a plastic picnic table. And so this demonstrates that what will actually be anticipated as a somewhat floppy structure in space can actually deal with floppy things on the ground. This beam combiner has been shipped off to Jacksonville, where Maiden Space is at, and we're now integrating the beam combiner with a prototype boom structure, and we will demonstrate that anticipated tip deflections of the outboard mirror units can be easily tracked out by the optical unit and the spacecraft. Now, what does this get you? What does all this effort get you? Well, you get down to milli-arcsecond resolution. In this case, we anticipate getting down to about 3 milli-arcsecond pixels for things that are very faint. I like to point to these lovely images that are coming out of ALMA of these YSOs with their disk structures. And basically this allows you to burrow into the inner central pixel of ALMA. And so at everybody's canonical favorite distance of 140 parsecs, that's about 0.4 of an AU is where you can look. And so all of these things that we've been seeing during these very great talks already tonight, we've been able to, we would be able to turn those from schematics into actual images of the central pixel of these sorts of things. There's other sorts of disk structures that are far away that you can look at as well, as far as the central parsec of nearby AGNs. The techniques that go into reconstructing images like this have been actually demonstrated for the last 10, 15 years with ground-based interferometers. With ground-based interferometers, we unfortunately have the limitation of the Earth's atmosphere, so we have to look at bright things, but bright things are still interesting to look at. We've been mapping the surfaces of stars and also mapping stellar binaries. Another application of this particular proposal would be to look at young stellar objects as well as low mass stars, things that are too faint to be looked at with ground-based facilities. And we would be able to do that in the visible and down into the near UV. This is a concept that we've been developing over the last actually 18 months or so with the lab work. And since we are going to try and transition this to a proposal for a small sat by the end of this year, we are in the process of trying to put together a science team. And so my question to all of you is, what would you do with this sort of milli-arcsecond resolution, but going down to very, very faint levels of, say, 17th magnitude objects? If you are interested in this and have ideas, I encourage you to give me a holler and talk about possibly joining our science team. And I am eager to hear from people who have clever ideas to do things with this clever technology. And so with that, I will take questions, and I appreciate your time.
We should be getting in the habit of that now.
Thank you.
Thanks, Gerard.
It's a bit of a change of pace with technology talk rather than a science talk here.
How does one, what is the deposition mechanism for something like that in like a zero-G environment?
So the mechanism basically is like a 3D printer here on the ground. It's using things, basically a PLA style printing, extruded printer. They've actually flown other technologies on board the space station of printing in other substrates like gel. But basically this company knows how to make things in space. And there are certain tricks to doing that and techniques that make it so that it's pretty unique technology with dealing with zero-G and then also zero-G in vacuum environments. But this is the really neat thing, is that it's very, very kind of sci-fi and out there and a really game-changing technology. But at the same time, it's flying. There are units that are flying in space, and I think that this is really going to be the interesting future of astronomical observatories in general. Is not delivery to space, but assembly in space of observatories, and then ultimately even manufacture in space.
That is so cool. That's like revolutionary.
Awesome. Oh yeah, it's a total game changer.
We have questions. We have a lot of questions. First, let's go with Guang Wei.
Hi. Yeah, fascinating idea. I've always been fascinated about a space sample telescope. So my question is, first, what's the order of magnitude cost? And the second is, what's the limitation of this 3D print space? Can we like print the whole Louvre in space, 20-meter telescope, or this is more like a smaller scale? Yeah, thanks.
So the idea here is, I think the astronomical community will go absolutely crazy for interferometry once they get their first taste. And at the same time, they are very reticent to jump into this technology. And so the idea is to get it into a bite-sized chunk of EmitX MOO, mission opportunity, and that's going to be the small sat package that's on the order of $70 to $80 million. And so the upper limitation on this is right now with this technology, you can print support structures of optics. I would ultimately like to see actually printing of mirrors in space, but that's probably a generation away. But right now, yeah, we are envisioning booms that are twin booms that are 10 meters in length. The structure will be quite floppy. We'll have many centimeters of motion of the tips, but we can track that all out, and we can reference against bright objects on the sky because we don't have the Earth's atmosphere in the way. And so the idea is to make this as manageable of a leap into this technique for the community as possible.
Sounds like there's lots of room for great discussion about this. So
yes.
With that, though, we must bring the session to a close. I'm going to pass this off to Evgenia for the next phase. Thanks, everyone.
Thank you so much, Lauren and everyone. And there are many more questions. I have questions for you too, Gerard. Maybe during the coffee break, we can go to GatherTown and do that. But we do have one more thing from Melody Cow, who has put together a few of the poster pops for you. So we will spend the next 5 minutes listening to 1 minute pops. If you guys haven't experienced the poster pop phenomenon, it's great. You get a 1 minute slice of the poster, and then you can go over to GatherTown and check out the poster in detail and talk with the presenters themselves. So I'll pass this on to Melody to share her screen.
All right, just give me 1 second to share the screen. Can everyone see this? Yep. Okay, great.
Hello, everyone. My name is Meng. I'm a research scientist at Lockheed Martin Solar and Astrophysics Lab and SETI Institute. In this study, we adapt the alternate solar model that has been extensively validated with solar observations to simulate the stellar corona of episode Eridani. We used multiple observations to constrain the model parameters. In addition, we derived the emission merit distribution and 3 line intensities in far UV range to compare quantitatively with observations. We also present the model CME dimming relationship for the solar case, which will be explored in the future for the stellar CMEs from episode Eridani. Welcome to my poster for more details about this study. Thanks a lot.
We are presenting a new way of measuring the UV flux rate during solar flares. It is based on the footprint of the solar flare on the upper part of the atmosphere, the so-called ionosphere, measured by crossing global navigation satellite multi-frequency signals. We have validated this new technique versus direct measurements from photometers like the one in SOHO-SEM, and it works quite well for strong, mid, and weak solar flares. It is presently in real time for the European Space Agency, and presently we are working on extending the technique for superstellar flares like the one of Proxima Centauri.
Hi, I'm Lauren Biddle, and my research is motivated by the problem that not many young, close-in planets are known to us. This is because stellar activity gets in the way. One thing we could do about it is to know thy star a little bit better and characterize the activity signatures that are seen in these systems. I'm presenting my poster on a case study of CI Tau, which hosts a hot Jupiter. The hot Jupiter pulses accretion on the timescale of its orbit, and this is seen in the K2 light curve. When we isolate the short timescale variability in the K2 light curve and analyze its amplitude, we find that the same periods are present. This indicates that accretion variability dominates the system brightness on all timescales. Additionally, this predicts a time correlation in UV and X-ray, which is a motivator for high energy small satellite missions. Please stop by my poster. I'd love to talk about it with you a little bit more. Thank you.
Hi, my name is Riccardo Spinelli, and I am a PhD student at University of Insubria in Italy. In this work, I and my colleagues studied the ultraviolet and X-ray emission and variability of LHS 1140, an M dwarf which hosts a super Earth in its habitable zone. For this purpose, we analyzed a set of observations performed by the SWIFT satellite. We measured the near ultraviolet flux and estimated the far ultraviolet flux. Compared to similar M dwarfs, we found that LHS 1140 is one of the least variable, and we did not observe any flares. Moreover, we highlighted the presence of a contaminant source near LHS 1140. Our work suggests that the low level and stability of the UV emission are currently insufficient to trigger abiogenesis on the habitable planet, but should be favorable for its present-day habitability.
Hi, I'm Ward Howard, and I'm excited to be with you and share about a missing piece of the habitability puzzle. M-dwarf superflare temperatures observed simultaneously with multi-facility, multi-wavelength monitoring. Using NASA's TESS and every scope array of small telescopes, we were able to observe 40 M-dwarf superflares simultaneously. Every scope flares are shown in blue, while TESS flares are shown in red. Because superflares are rare events, this remains the largest sample of high-cadence multi-band flares seen to date. Using these flares, we were able to estimate the blackbody temperatures of the flares, assuming that the multiband observations accurately trace the flare spectra, finding temperatures as high as 42,000 Kelvin. We were also able to build scaling laws in our sample between flare temperature and flare energy. And finally, to place habitability constraints on rocky planets orbiting young M-dwarf flare stars, finding that 10 to the 3 watts per meter squared during superflares were possible. Please check out our work.
Alrighty, that's it for the first set.
That's
Good job, everyone.
Thank you, Melody, for putting those together and for everyone sending that in. I think we're perfectly on time, and we're going to have a break now. Everyone can do their jumping jacks, get a snack, whatever needs to happen. And we will be back. What time are we going to be back? Back at 10:40. At 10:40 Pacific time with Amanda Hendricks. So enjoy your break, and we'll see you soon. Thanks very much, everyone. Oh, we're all coming back. Hopefully that was a refreshing break.
Yeah, I just had part of my dinner.
I know. No real lunch or dinner break today. Hi, Amanda. Thank you so much for giving an invited talk.
Oh, I'm happy to be here. Thank you.
I'm sorry we don't get a chance to meet in person, but nice to meet you.
Maybe next time.
Next time.
All right, it's 10:40 here on my clock, so we can resume our session. This is going to be a session on the solar system. And first of all, I just want to say that I'm very happy to see so many people here that I usually cite on my papers, but I haven't met yet. So it's very nice to see your faces now. Maybe I'm going to the wrong conferences. I don't know. Maybe I'm going only to exoplanet conferences, and that's not the best option. All right, so please remember to raise your hand when you want to ask a question. And if we have an overflow of questions, you can ask in the chat. And also remember at the end of a talk, remember to turn on your mic, unmute yourself, and join the clapping. And yeah, we can start with our invited talk by Amanda Hendricks. And so please take it over.
Great, thanks so much. I'm gonna share my screen. And hopefully you can see this now in slideshow mode.
Yep.
Great. Okay, I'm gonna start my timer here so I can keep track. Okay, so shifting gears a little bit from the last session to move to the solar system. And I'm going to focus here on solar system surfaces, which is the focus of my research. And in terms of solar system observations, in my mind, a lot of the key historical observations have been done with IUE and HST, and also deep space probes like Galileo, Cassini, Messenger, the Mariner missions, and a lot more. I won't try to list them all here. But a lot of the earlier studies from several decades ago focused on planetary observations of planetary atmospheres and aurora. And in more recent decades, UV instruments have kind of started focusing a little bit more on solid surfaces, including thin atmospheres and plumes. And I credit some of the early observations mainly done using IUE, but also Mariner 9 and OAO2 by some of the references that I list here as being really kind of groundbreaking in getting some of those types of observations started. But these UV observations of surfaces are really important because we can learn about space weathering effects on these bodies. There are diagnostic absorptions in the UV that we can learn about that can be then correlated with, for instance, near IR observations. We can learn about thin atmospheres, search for and discover plumes, and in general, just do complementary and new science in the UV. So here I'm going to focus on Saturnian satellites, C-complex asteroids, and the moon, using data from the Cassini ultraviolet imaging spectrograph, or UVIS, using IUE and ground-based data, and also the Lunar Reconnaissance Orbiter Lyman Alpha Mapping Project, or LRO LAMP. And I'm going to kind of fly through these because I have a lot to share. Okay, so let's start off with the Cassini observations in the Saturnian system. So Cassini spent 13 years in the Saturnian system from 1997 to 2004. And we got a lot of great data of the inner icy moons of Saturn, Mimas, Enceladus, Tethys, Dione, Rhea, that all orbit Saturn within this very broad, tenuous E-ring made up of fine grain, mostly water ice, particles that emanate ultimately from the Enceladus plume. And we had known even since the Voyager days that the albedos of these moons, even before we knew where the E-ring emanated from, what the source of it was, that there were trends between the geometric albedo of the moons and the brightness of the E-ring. And so these are some early Voyager measurements, and then HST measurements that show the effects in a little bit more detail. And so I've been really interested in studying these E-ring grain effects in the UV on the moons. In the UV, for instance, Enceladus has a spectral shape that looks like this here. And pretty much anywhere where we look in the Saturnian system, that's a solid surface, has got this strong absorption here at about 165 nanometers, which is due to water ice. And one of the first, if not the first, detection of water ice in the UV was made down here at the lower right using IUE on the Saturnian rings. But we've used this diagnostic feature throughout the Saturn system to help us understand water ice, its abundance and grain size. And on Enceladus, you can see here in this plot here, hopefully you can see my cursor, the albedo of Enceladus looks a lot like water ice, but much more muted. It's not nearly as bright as it ought to be if water ice is all that's there on the surface, which was a big clue to us, because at VIS near IR wavelengths, the surface of Enceladus pretty much looks like water. But we could see that because Enceladus is actually a lot darker in the UV than water, that there must be something else present on the surface that's helping to absorb the light there. So here are some composite spectra using data from other instruments on Cassini, the VIS and near IR instruments, showing the whole composite. These are normalized reflectance spectra on the left and geometric albedos on the right of all of the satellites, and mostly for both the leading and trailing hemispheres. And so we can see that, yes, they all actually absorb in the near UV going down into the far UV. And this is telling us something about the composition of the surfaces. And it says that it's not just water ice that's on the surfaces. And so what we've done is looked at the exogenic processes going on in the system and how they link to this UV absorption that we see, and also to the albedo. And so we looked at the E-ring grain flux onto the surfaces and compared the E-ring grain flux with that absorption depth, that UV absorption depth. And we also looked at, on the next slide, the electron intensity. So the kind of cold plasma that bombards the trailing hemisphere of these bodies. How does that impact the albedos and the UV absorptions? And so what we found is that there's a relationship, there seems to be a relationship between the UV absorption, which seems to increase with decreasing E-ring grain flux, and also that the albedos decrease as electron intensity increases. So there seem to be some relationships here. And also we can look at, this is just a quick look at a UV image on the right-hand side, Cassini UVIS image. This is at about 180 nanometers of Dione. So one hemisphere of Dione. And here on the left is a visible image. And on the next panel over, if you can see my cursor, is from VIMS showing the water absorption strength. And we can see some correlations here. Here's the E-ring grain dust deposition model, or one of the models that's out there. And in general, so what we find from all of these kind of correlative studies is that there are relationships between the amount of E-ring grains hitting anywhere on these surfaces, and also the amount of cold plasma bombarding the surfaces. And so just to kind of give you kind of a high level summary, what we find is that there's a link between the UV absorption, so the redness of the surfaces, and the E-ring grain flux and the magnetospheric bombardment. And we find that the regions that have lower E-ring grain fluxes, and this is mainly regions on the moons that are farther away from Enceladus, have stronger absorptions. They're redder and darker than regions with higher E-ring grain fluxes. So places like Tethys that are closer to Enceladus. And importantly here, what we found is that organics actually make up some 25 or 30% of E-ring grains. So it's not, I don't mean to imply that 25% of the grains are organic rich, but there is some component of organics in 25% of those E-ring grains. And we know that when those organics get exposed to UV and charged particles, that they get darker and redder. And so we think that it's this organic component of the E-ring grains that get deposited in varying levels across these moons that is acting to color the surfaces of these moons. So this is one area of study that we're still into, but it's pretty interesting. And furthermore, oops, let's see, I want to go to the next slide. I want to go here. Speaking of organics and their responses to processing, carbons are spectrally active in the UV. And so not only in the near UV where we see kind of a reddening in response to, say, irradiation of hydrocarbons, but graphitization and carbonization of these species can lead to very diagnostic spectral features, and even at shorter wavelengths, so getting down into the far UV. So this plot here on the left shows terrestrial samples. So some coals of varying graphitization levels. And you can see that as you go up, these are offset. As you go up here on this left-hand slide, you get more and more graphitized, and these spectral features out here become more and more intense. And so we can perhaps use these signatures to get an idea of how relatively old a carbon-rich surface is and how exposed it's been. And this overall kind of change in slope here that we see that may be related to the level of carbon on the surface and its graphitization could be linked to some of these asteroids that we see, like Ryugu that's visited by the Hayabusa 2 mission, and Bennu that's visited by the OREX mission. These are both near-Earth asteroids in the C complex family that are both spectrally kind of blue. And perhaps this is because of a carbonaceous component of the surface and the processing of that. Okay, and also on Ceres, I should say, we do see this very unique spectral feature out here at about 160 nanometers, which could be due to a graphitized carbon. Okay, now let's go on to the moon. So I've talked about water ice and hydrocarbons and carbons, and I want to come back to water ice on the moon because the LRO LAMP instrument has found evidence of water in the lunar polar regions, particularly in the PSRs. And what we've also done with that instrument, it's an FUV spectrograph, is we have taken data of the at lower latitudes, so away from the permanently shadowed regions in the poles, and we're looking at daytime data, so solar reflected signal. And again, we're using this strong water absorption feature. It's so strong that for intimate mixes modeled here, if you just add a little bit of water to a lunar regolith type stuff in a model, you'll need a little bit of water to make a pretty obvious and detectable change in spectral slope here at around 165, 170 nanometers. And as a matter of fact, we can use this. We measured spectral slopes across the surface with LAMP and look for variations in slope that might be due to water and might be varying with time of day and therefore temperature. And so this is what we have done, and we're continuing this study, but we looked initially at two regions, a big highlands region here and a big mare region here. And this plot in the lower left here shows you those spectral slopes, again, measured in this 165 to 173 or so nanometer region.
2 minutes.
And we looked at those spectral slopes versus time of day. And especially for the highlands region here, we see, okay, it stays pretty constant, but then around local noon, there's a dropout and then it comes back up. And it turns out that this is actually consistent with lab results, lab measurements of highlands samples that have been sort of dosed with water. And it's consistent with adsorption, cryosorption of water on the lunar regolith and desorption with temperature. And so we can model this. Over here on the right is shown these spectral slopes versus temperature now, as measured by the Diviner instrument on LRO. And we can model it using different activation energies. So that describes how kind of strongly these grains hold on to water molecules. And then we can get an amount of water that might be distributed across the top of the regolith. And it's very small. Again, this is a sensitive way of measuring water. It's less than a percent of a monolayer. A monolayer is about 10 to the 15 molecules per square centimeter, and we're measuring less than 0.5% of a monolayer that then desorbs at local noon and then resorbs later. And so it might be, you might imagine something like this where water molecules desorb at the hottest time of the day and then might bounce around on the surface. And so just to kind of summarize these LAMP results, again, we're kind of determining the activation energies that might be required to hang on to this amount of water at these temperatures, but it's consistent with desorption at midday. And this is also consistent with the idea of water being transported around the surface and ultimately ending up in those polar permanently shadowed regions where the water is stable for long periods of time. So just to wrap up, I've kind of flown through these topics, but we're using UV spectroscopy in the solar system to look at these kind of wide scale trends on airless bodies, like the Saturnian satellites, the moon, asteroids, and other kind of carbon rich regions in the solar system. And so the focus that I've been talking about is mainly on water and carbons, but there's also work going on with other ices and volatiles that have diagnostic spectral signatures, irons and iron oxides. We have a SURVEY, which is a virtual institute through NASA. Our TREX team focuses on the characteristics of fine particles that ought to be covering a lot of these airless bodies from the deep UV clear out through the mid-IR. But I list here a few researchers in the community who are doing a lot of great work too. And I encourage you to check out their work too, because I've kind of focused on the stuff that I've been doing, but there's a lot of other great work happening out there too. Again, we're looking at space weathering and compositional trends in the topmost layers of the regolith. And hopefully we'll have more UV instruments and observations on future missions and also additional lab work. So I will wrap it up right there and take any questions. Thank you.
All right, thank you. We have one question in the chat. Do you want to ask? Word?
Well, sure. That was a great talk and really, really fascinating. I was wondering if angular resolution or signal to noise constraints could allow for carbon chemistry or other space weathering phenomenon to be seen in the UV from extrasolar materials.
That's a great question. I've been kind of wondering something like that too. I think that it's worth a study to look at what kind of angular, I mean, I would think that both of those things would be, kind of tight. Depending on what you're looking at in terms of the size of the object, obviously you need your angular resolution, and then hopefully you can get a lot of observing time so that you can get good signal to noise, like integrate for a long time or do a bunch of exposures to co-add them. I think it's definitely worth giving it a shot though. But of course, a lot of the carbon work that has been done in the lab is based on the 217 nanometer feature seen in the ISM. So I think it's worth kind of extending some of those types of applications.
All right, we have time for one another question because I rambled a bit in the beginning. So please go ahead, Virginia.
Very quick one. Thank you so much, Amanda. I learned a lot because it's outside of my normal work life. So all these instruments, if I heard you correctly, they're all in situ, right? They're all there, right? Yes or no?
Well, except for IUE and HST.
Right.
But the C complex asteroid work that we've been doing has been based on IUE data, but also combining with ground-based data. But yes, all of the other ones pretty much are deep space, missions that are there.
So looking toward—
Both are important.
Both are important. Okay. All right, I'll leave it at that. Thank you.
Because we're going to need another space-based UV telescope before too long.
Right, you can do a lot. I guess my point is you can still do a lot with HST and not always need to be there.
Absolutely.
That's what
Absolutely. We cannot actually do everything there. Right. Like for getting context and for finding out what we need to do when we're there. You need those kind of initial observations and disk integrated observations of some of these targets that you can't get.
Both, but you need both.
Yep.
From perspective, we need both. Okay, that's what I was trying to get at. Thank you.
Thanks for bringing that up. I think that's a really important point.
All right, thank you, Amanda. I'll have a question for you, but I'll ask in the chat because next up we have Kevin Stevenson. So please go ahead. You have 7 minutes.
All right, thank you. All right, 7 minutes is quick. All right, thank you very much. Let's see if I can get the full screen going. Here we go. All right, I'm excited to be talking to you today about a mission concept called Star Helix. About a year ago, we were thinking about what sort of exciting science we could do with the solar system planets in terms of treating them as exoplanets. This is a group of us at Johns Hopkins Applied Physics Lab. And the question that we came up with, and I'll pose here for the audience, is if Earth was an exoplanet, could we tell whether or not it was habitable or even inhabited? Of course, we all hope that the answer is yes, but if not, how can we expect to find life in other systems in the galaxy if we don't even have the tools necessary to detect life on our own planet? So here I'm showing you the 4 guiding scientific questions in our quest to find extrasolar life. Now, you might be familiar with the challenges associated with stellar atmospheres and how they contribute as a source of uncertainty to our measured spectra, and the great ways that people are working to solve those issues. So I'll talk a little bit about stellar variability, but I also want to focus on planet variability, which you may not be as used to talking about. Here, I want to talk about variability in transmission spectra due to clouds and seasonal variability, and essentially the impact that could have when we're stacking our transmission spectra over potentially years worth of observations of an exoplanet. And of course, the big question that we're trying to address here is, can we find signs of life on a system for which we already know the answer? So here I'm showing you a simulated Earth transmission spectrum from a spacecraft at a distance of 0.03 AU from the Earth. Now on the left-hand side, you can see the Earth-Sun system at that distance, and it's shown to scale. So the transit depth is roughly 10%. Now, just for comparison, on the right-hand side, I'm showing the TRAPPIST-1 system with TRAPPIST-1e transiting in front, and that's a transit depth of about 0.5%. So from our spacecraft, we're able to obtain a transmission, we would be able to obtain a transmission spectrum of the Earth that has 100 ppm, 1 scale height feature sizes. This is 5 times larger than what we get in the TRAPPIST-1 system. So we'd readily be able to measure, for example, habitability indicators such as water and CO2, and also biosignature pairs such as oxygen and methane or ozone and methane. Now, ozone has very strong features in the UV, so it really gives us an opportunity here to think about what sort of measurements we could do in the optical and the UV in order to constrain the spectrum of the Earth and answer some of these questions that we've been posing. Now, the question, first of all, is how variable is this transmission spectrum? So let's see if we can quantify that over the next couple of slides. First of all, let's talk about stellar variability. The transit light source effect is potentially the largest signal or source of variability that we have to contend with. This is due to the appearance of spots or faculae on the surface of the star that can essentially mimic atmospheric features. They would alter the observed transmission spectrum. The problem, of course, is that we can't visibly resolve the surface of a distant star, so we have no idea whether or not what fraction of the star's surface is being covered by spots, whether or not the planet is transiting across some or none of those spots. The figure on the right here at the top right is showing the relative transit depth and how it varies depending on the level of activity in the sun. So you can see there are hundreds of ppm difference in the absolute transit depth just based off of that variability. And the source of the signal size is depicted in the bottom right-hand corner there. So really, even for a quiet star like the sun, these effects can't be ignored. Now, turning our attention to planet variability, I'm showing you here reflected light variation due to the rotation of the Earth. You might be familiar with this observation or this map from Jacob Lustig-Yeager. Basically, it varies depending on, you have whether you're looking at continents or oceans. You can see that the variation in the continuum as it probes, through the clouds or not, and maybe the 0.7 micron vegetation edge there. This is a great representation for reflected light, but we don't have something similar, a certain time-dependent transmission spectrum of the Earth, which is really key for understanding what the potential variability is. Recently, McDonald and Cowan published an empirical clear sky transmission spectrum from 2 to 14 microns using solar occultation data, which is a really clever way of obtaining the transmission spectrum. But what we're missing here, of course, is UV optical and that time variable impact of clouds. So this is what we're looking at here when we talk about the impact of clouds. I'm showing you 3 spectra: clear sky, the stratocumulus clouds, and cirrus clouds. And the Earth's spectrum at any given time is going to be some combination of those 3. And really what we want to do is make this measurements to determine that based off of different timescales, hourly, daily, even seasonal variability that could potentially impact the measured transmission spectra on other exoplanets outside our solar system. So to tackle these questions, I'm going to suggest a star helix, a mission concept that would go beyond L2 in order to induce transits of the Earth across the sun. And it will enable us to quantify the effects of stellar and planet variability on the measured transmission spectrum using the ground truth, the information that we already know about the sun and the Earth. And it will also validate that mechanism of stacking or co-adding dozens of transmission spectra as we search for biosignatures on M dwarfs with, for example, James Webb and future mission concepts. So how do we know this ground truth? Well, here I'm showing you on the left a movie of Earth's water vapor spanning about a week in time. And on the right is about a similar amount of time showing the sunspot variation. And remember, we have all of this information available to us, both not in time, but also in space. We can spatially resolve the surface of the sun. This will allow us to disentangle degeneracies that we have normally with transmission spectroscopy observations of exoplanets where we can't resolve that. So using that information, we can potentially learn how to resolve these essential degeneracies or sources of variability and apply that to other systems. So I don't have time to go about this in detail here, but the point I do want to get across is there is a strong dependence on where you are in the system. L2 point is 0.01 AU from the Earth, and that's a very deep transit depth. What we want to do ideally is situate ourselves closer to 0.03 AU. This is where we get that 10% transit depth that I've been talking about earlier. And the key advantage to being out there is that we don't spend too long during ingress and egress. If we are at that sort of close to L2 point, the transit depth looks a little bit too V-shaped. And as we go out to 0.03 AU and further, we get more and more time during full transit, which is important. All right, I'll skip over that slide. In conclusion, the Earth Transit Observer can potentially solve open questions about star, planet, and detector variability. The solar system is really the only place where we can translate the removable features we see on a planet with the disk integrated or annulus integrated observations we get of exoplanets. And so it's really necessary and even critical that we do these experiments here where we have the right answers to make these connections. Thank you.
That was cool, Kevin. Thanks.
Yep, thank you. We have one question. Laura?
Yeah, hi. I mean, since this is UV conference and all, how short would this go and what would you expect to gain from the UV observations that you wouldn't be getting from optical and stuff?
Ideally, we're hoping to go out to 250, down to 250 nanometers. The reason being is that we want to detect Rayleigh scattering, such as the slope in the atmosphere, and also ozone higher up in the atmosphere to make that biosignature detection of ozone plus methane.
All right. Next, we have John.
Yeah, so thanks. It's a really neat idea. I was wondering about the proposed Earth transit chord across the sun and how that might be varied in terms of the active longitudes on the sun and how much you can vary that during the experiment to test, occultation of star spots and the effect from the transit light source and on the transit. And the inferred,
yeah, we ideally we'd want to be off the center of the core of the sun a little bit in order to cross the stellar features, the spots and faculae of the sun as it becomes more and more active. There is some level of control with the spacecraft that would be able to apply in order to achieve that. And ideally, if you had a slight sort of inclination in our orbit, as you go further and out, you go higher and higher up, essentially increasing the impact factor as the planet crosses the star in order to get multiple transit at multiple impact factors across the sun, which I think would be really interesting scientifically.
Okay, thank you. So next we have Michael Chaffin.
Hey.
All right, I see. All right, you can go ahead.
Cool. So I'm going to talk about hydrogen and oxygen loss at Venus, Earth, and Mars. There's a lot of literature on this subject, as you might imagine. So this is going to be a short and idiosyncratic summary of the major loss processes that matter at each of these solar system planets. So we know that hydrogen loss has been extremely important in the history of Venus and Mars. Oxygen loss has also been very important at Mars. And when we think about applying the lessons we've learned in the solar system to exoplanets, we need to recognize that there are important boundary conditions in photochemical models or in other models of these exoplanets that should be informed by what we know about the solar system. So let's start with oxygen, because I think the oxygen story is a little bit easier than the hydrogen story, which I'm going to spend most of the talk on. So neutral oxygen loss at Mars, where it's been most significant among these three terrestrial planets I'm talking about, is mostly via dissociative recombination. So this is a process, an ionospheric process, where the oxygen atom gains the 3.8 EV it needs in order to escape the planet. And it does so through this recombination of the O2 plus ion and electron, which leads to a dissociation. And that dissociation can put the atom into a bunch of different electronic states, some of which give the resulting atoms enough excess translational kinetic energy that one of them can escape, the one that's pointing up. And at Mars, this has led to the loss of about 460 millibars over solar system history. We know this because we've made observations with MAVEN, and here's one of those observations in the ultraviolet at 130.4 nanometers, showing this hot oxygen produced by this photochemical process as a kind of haze surrounding the planet. Closer in is the thermal oxygen, which is very tightly bound. So you can only get up to 7 EV from this particular process, and most of the processes that are similar have similar upper limits on the energy that they can provide, which means that at Earth and at Venus, this particular mechanism doesn't provide enough energy for escape. Ion mechanisms are required, and I'll let Dave Brain, who's got the next talk about those. Sort of shifting from oxygen to hydrogen escape, one thing a lot of people talk about in the literature, especially for Mars, is stoichiometric balance. And this is the question of whether the oxygen loss balances the hydrogen loss. Any imbalance leads to surface or atmospheric oxidation or reduction with astrobiological implications. People talk a lot about false biosignatures from oxygen resulting from the hydrogen being lost with the oxygen retained. At Mars, because you can have both oxygen and hydrogen escape through mostly neutral mechanisms, McElroy in 1972 suggested that the oxygen escape is balancing the H escape in a 2-to-1 ratio, that stoichiometric ratio of water. But in fact, this results from a couple modeling assumptions, and you can see them here. In order to get this result, you need hydrogen and oxygen to be the only escaping species. You need water to be the only major surface source of hydrogen and oxygen that escape. And importantly, you need the atmosphere to be in a steady state, which means that you don't get large oscillations or long-term changes in the state of the atmosphere and the insulation. For Earth and Venus and for Earth-sized exoplanets, the O can't escape significantly via neutral processes. So these arguments don't apply, although if you include ion loss processes and allow your photochemical model to do a self-consistent calculation, you'll probably get the same result just because these assumptions are so generic. Moving on to hydrogen escape. So a lot of people assume that hydrogen escape is easy because hydrogen is light, and that the hydrogen loss should sort of depend upon the flux that comes in from the star. So if you have more flux from your star, you should have more hydrogen loss. But this is not the case for the terrestrial planets in our solar system. So a lot of people look at this formula for Jeans loss, where the left-hand side gives you the flux of escaping atoms. And they say, well, I've got temperature in the bottom, but it's in the exponent here. So I should have a really strong dependence upon the temperature. If I increase the temperature, the loss rate should go up by an exponential amount. But actually, in point of fact, this is only the case if the H loss is limited by the escape process. In reality, H loss at the Earth and at Mars is limited lower down, either in the thermosphere or in the transition from the troposphere into the upper atmosphere. And in fact, if H loss is limited in the thermosphere, you get an inverse response to increasing temperature or increasing solar EUV. And that's because the hydrogen has to fight against the much hotter thermosphere, which is trying to make everything collisionally follow the mass of the heaviest, the most abundant species, the heavier species in the atmosphere. And so if you increase the temperature for the Earth, you actually get less hydrogen escape if the limit is in the thermosphere. But in point of fact, the limit for both Earth and Mars is lower down, and it's the diffusion of methane across the troposphere to stratosphere cold trap that likely limits hydrogen loss. On Mars, there are other limits. It used to be thought that it was molecular hydrogen, but these days we think that there's significant transport of water directly into the thermosphere. And so if you increase the illumination of your object, the H loss will respond instantaneously, but the long-term average loss rate won't. The inventory in the thermosphere will go down in response to your change, but you'll get essentially the same amount of loss as you would over time, because the limit comes from lower down in the atmosphere. So I have a couple more slides on thermal hydrogen and non-thermal hydrogen loss. And the point of this slide is to show you that for Mars, with an exosphere temperature of around 200 Kelvin, you get a substantial amount of thermal hydrogen escape today. At Earth, the much higher gravity is balanced by a much higher thermosphere temperature, which means that you can still get significant thermal escape. But at Venus, the thermosphere temperature is cold, similar to Mars. And the high mass means that thermal H loss is extremely inefficient. So the take-home point here is that Venus can't lose H thermally. You need to appeal to a different mechanism. And the mechanism for non-thermal H loss at Venus and the dominant process at Earth is charge exchange. Ionospheric charge exchange, where you have hydrogen, the hydrogen ion, the planetary hydrogen ion, high up, colliding with a neutral, stealing its electron, and becoming an energetic neutral, which carries the ion temperature, which has a translational kinetic energy that's higher than the neutrals and can therefore escape more easily. At the Earth, this process happens in the Van Allen belts, in the radiation belts, as a result of collisions and interactions with the neutral hydrogen exosphere. And in addition, at the Earth, there's this other process, the polar wind, which results from an ambipolar electric field near the poles. So I'll leave this slide up and finish with some prospects for cross-planetary synthesis. Because I think I'm a little over time, I'll just let you ponder these questions, and I'm happy to address any of them either live now or in a follow-up on chat. Thanks.
Thank you, Mike. We have time for one question or maybe two if they're fast. If not, I actually took note of 3 questions that I could ask, but I'll give you 3 seconds. All right, then I'll ask. Mike, so do we have in the solar system an example of atmospheric escape that we could extend to planets that are similar to super-Earths or sub-Neptunes, or super-Earths that still retain part of the primary atmosphere?
So you're thinking about a planet where the gravity is stronger than the Earth's gravity?
Yeah.
So in that case, you would need to use probably a non-thermal process. It's my understanding that there is a lot of excess energy in these ionospheric processes that operate at the Earth. So in this ring current, you can accelerate ions, including H ions, up to really high velocities. And then through a collision with a neutral atom, you produce an energetic neutral that no longer has to follow the magnetic field. And that can produce a beamed energetic neutral. And actually, this figure is from the TWINS instruments, which have some energetic neutral atom imagers and have been collecting data about this process in particular at the Earth for almost a decade now. So I would appeal to a process like that, or possibly to one of the ion processes that Dave's going to talk about.
And what if it's a super-Earth that has less gravity? Suppose that it has a puffier primary atmosphere.
Yeah, so then you start to cross the threshold between Jeans escape and hydrodynamic escape potentially. As hydrogen starts to become a major constituent, these arguments that I made about hydrogen being trapped lower down become less applicable. And all of a sudden, if you have a majority hydrogen thermosphere, for example, it becomes very hard to cool that thermosphere. That's why the gas giant planets in our solar system have such hot thermospheres. And so there's potentially a region where you could have steady state hydrodynamic escape, possibly. But I don't know that anyone has explored that. Of course, I'm not familiar with the exoplanet literature. So if you've done that and you're in the audience, please educate me.
Leo Corrales has one question, but it has to be fairly quick.
Yeah, I just had a clarifying question about the charge exchange mechanism for Venus. Are you saying that that's the dominant mechanism for hydrogen escape now or in the past?
It's the dominant mechanism today. So thermal hydrogen can't escape Venus. The Venus thermosphere is just too cold. So the translational kinetic energy of a thermal neutral hydrogen atom in the atmosphere is not large enough to escape. The lifetime against escape via Jeans loss is a couple billion years, I think. So instead, what happens is you make planetary protons, they get high up, and then they charge exchange with a neutral. And because they have a higher kinetic energy by virtue of ion acceleration processes that happen in the planetary atmosphere, they can then escape.
Okay, I'd love to pick your brain about it later. I'll find you later.
Yeah, and I mean, one question that I'm super interested in is, like, we know that Venus lost almost all of its initial hydrogen as part of its runaway greenhouse process. So was that H removed by the same process that's operating today, or do we need something that's more efficient potentially in order to remove that hydrogen?
Thanks.
Thank you. Let's move on. So next up, we have an invited talk by Dave Brain. And we have 15 minutes with 5 minutes of questions.
All right, thanks very much. So I'd like to talk about the atmospheric response of unmagnetized planets to stellar EUV. And I'm going to share maybe 3 or 4 main points in our time together. If I can get all the windows organized. Yes. So first, a very basic point that the stellar EUV flux creates induced magnetospheres. And this is a subset of the kinds of magnetospheres that we think of and experience in the solar system. So Janet Lumen in 1987 made this nice set of very basic cartoons that does a great job explaining what an induced magnetosphere is. First, any planet with a neutral atmosphere has those particles that are gravitationally bound to the planet. And when exposed to solar radiation in the form of extreme ultraviolet flux and X-rays as well, will ionize. And so you'll get an ionosphere at the top of the atmosphere of that planet that sort of straddles the thermosphere and the exosphere. This happens regardless of whether the planet has a magnetic field or not. But in the situation where the planet lacks an intrinsic dynamo magnetic field, the presence of these charged particles in the upper atmosphere ends up creating a magnetosphere of its own. And that's because those charged particles can flow, and they can flow in response to the incident solar wind, which carries a magnetic field. So a time-varying magnetic field will induce a current. That current itself will create a magnetic field that offsets the magnetic field being carried by the stellar wind, and you end up with a magnetospheric interaction where the magnetic field lines carried by that stellar or solar wind drape over the conducting ionosphere, which shields the solar wind out. So this is a special kind of magnetosphere not formed by an intrinsic dynamo inside the planet, but instead formed by the interaction between the upper atmosphere and the solar wind itself. And this magnetosphere can be consequential and participate in all sorts of space plasma processes, including, in some cases, influencing atmospheric escape and how that works. So maybe a more up-to-date picture of what this kind of magnetosphere may look like is this cartoon here for Venus, where you can see various plasma boundaries and yellow magnetic field lines draping over the ionosphere, in contrast to Earth and its global intrinsic magnetosphere. And in most cases, induced magnetospheres form close to the atmosphere that the stellar wind or solar wind is interacting with. Another big difference between these magnetospheres is the fact that induced magnetospheres reorient in response to changes in the magnetic field in the stellar wind. My dog is participating in the talk. So as this magnetic field reorients, since it's the one that's helping to create this magnetosphere in the first place, the entire magnetosphere can twist and reorient and turn around. Okay, the solar system has many examples of induced magnetospheres, and here they are shown somewhat to scale for the various induced magnetospheres that are known. And as I said before, most of them form close to the planet, and most of them are through interaction with the solar wind, although Saturn's moon Titan has an induced magnetosphere that forms inside the Saturnian magnetosphere. So the plasma here is inside Saturn's magnetosphere for something like 95% of the time. The one exception here to this small scale size of the magnetosphere is for comets. And I was careful on the last slide to say that it's the interaction of the stellar wind with the atmosphere itself. Comets, especially as they get closer to the sun, have enough atmospheric mass loss that makes the magnetosphere very large relative to the size of the object. So here are a list of some of the properties that influence induced magnetospheres. Okay, topic number 2, stellar EUV drives escape from planets, but it's not the sole driver. So Mike did a great job talking about some of these escape processes, and so I will skim through some of this. But a rule of thumb for checking on whether thermal escape is going to be important from a planetary atmospheres, and then whether an extreme form of thermal escape, hydrodynamic escape, is going to be important, would be to examine something called the escape parameter, simply a ratio between the gravitational energy and the thermal energy of the particles in the atmosphere, such that low values of the escape parameter indicate that escape is going to be very likely. When you write out these terms, you see that significant thermal escape is favored when the temperature at the exobase is large, when you have a low mass species, such as hydrogen in the atmosphere. So this is especially important for primordial atmospheres, and also when the mass of the planet is low as well. Okay, but there are occasions, especially in our solar system today, for which hydrodynamic escape does not occur, in part because exospheric temperatures have cooled, and in part because the secondary atmospheres are much more massive. So then we have to examine a series of other atmospheric escape processes, and depending upon how you think about them, you can classify them into a number of processes ranging somewhere between 4 and 8 or 9 processes. So I'll walk you through those very briefly, and we can call out where ultraviolet plays some role in these processes. Again, a planet with an atmosphere, in this case, a very extended atmosphere, is going to form an ionosphere, a layer of charged particles. And those charged particles will feel the electric field carried by the stellar wind, and therefore can gyrate away from the planet. And so there are many different electric fields that can accelerate ions away. Mike mentioned one in the last talk, the ambipolar electric field, but there are at least 2 others that play important roles, and we tend to lump all of these together in the ion escape category. Ion escape can happen for all species, but for planets like Venus, as Mike mentioned, and Mars as well, it tends to be most important for massive species, oxygen, atomic or molecular. Sputtering is a process as well, where you have ions that are trying to escape away from the planet, but the planet is in the way. And so these ions go crashing right back into the atmosphere and can splash entire other particles out, both neutral and charged. Again, important for heavy species. Photochemical escape, Mike talked about in the last talk, when UV light can drive dissociative recombination in the atmosphere. Those dissociation products have enough energy for small planets like Mars to escape the planet. For large planets like Venus or Earth, then it can't work, and you have to appeal instead to charge exchange. Finally, thermal escape, which we've already mentioned in this talk and the last talk. There you have a velocity distribution of particles in the upper atmosphere. Some part of that velocity distribution should exceed the escape velocity. Again, important for low mass species, things like hydrogen. So given all these, we can take measurements that have been made at various planets, and the MAVEN spacecraft currently orbiting Mars is arguably the best data set for atmospheric escape in the solar system. We have the best measurements there. So we can look at how all of these processes combine with each other, both during quiescent times and during very active periods for at least present day sun. So I'll just share with you about 3 results on these escape processes. First, Mike already mentioned photochemical escape, so I won't dwell here, but I will show you the data a bit. This is the escape flux of oxygen due to photochemical processes driven by EUV sunlight and organized by the ionization frequency, or analogously, the strength of the EUV flux. And we can see that the larger the ionization frequency, the greater the escape flux is from our calculations. And there are arguments about whether there should be a linear fit to this curve or some sort of higher degree polynomial fit. Depending upon which fit that you prefer, you can extrapolate back in time, back in solar system time. The present day escape rate is given by the blue line, but if instead you fold in the EUV dependence, you're going to get much greater loss at earlier periods in Martian history. And this is where Mike got that number of 460 millibars, assuming the best fit dependence to EUV flux. We're headed now into solar max, so we're going to see how this curve evolves at even larger values of the ionization frequency over the next year or 2. Next, ion loss, which we promised that I would talk about. Ion loss is observed at Earth, at Mars, and at Venus. All 3 of these panels here are drawn to scale, and the sort of gaudy rainbow color bar gives you a sense of the flux of oxygen escaping each of the planets, where warm colors indicates high flux. So it's observed at all 3 planets, even though Earth is magnetized and Venus and Mars are not. And the escape fluxes are surprisingly within an order of magnitude of each other, at least to 0th order. More recent work for Mars, and I know this is a messy plot, shows that the dependence of ion escape on the solar EUV is maybe not so simple. So the x-axis is the EUV flux, how much EUV is coming from the sun. The y-axis is the escape rate. And I'll just focus your attention on the green data points. Again, we don't have a lot of data at high EUV, so we'll be filling this in the next couple of years. But it turns out a linear fit to the data doesn't do as good a job as some kind of a polynomial fit with just one extra term compared to a linear fit. And it shows that as EUV flux increases, there may be a limit to the amount of ions you can pull out of an atmosphere. Making things brighter doesn't necessarily help a whole lot when you get to really bright EUV fluxes. And this is not that bright for our sun. However, when we look at not just Mars, we look at Mars, Venus, and Earth. This is a plot that I've been showing recently from Robin Ramstad, showing how the solar wind dynamic pressure plays an important role in the escape rate from these planets as well. And this should be, for exoplanets to 0th order correlated with the EUV flux from the star, but not exactly the same. And we see that Earth has a very strong response to the solar wind pressure, whereas Mars and Venus responses are either weaker or much more complex. Folded into this diagram where I've shown in broad swaths, the blue, the yellow, and the red, if we take those away, you can see that there are multiple traces for each planet, one for low EUV and one for high EUV for each planet. The EUV dependence, the EUV control of ion loss rates is actually a perturbation on the solar wind dynamic pressure control of loss rates. That's the dominant controlling factor, especially for Earth, and then the EUV provides a small perturbation on this. Okay, topic 3, briefly, stellar flares heat upper atmospheres, driving escape. This is an obvious point to make, but I'll show you a couple of observations. First, an MHD simulation of the entire inner heliosphere with the sun at the center, Earth here, Mars over here. And this simulation was provided by NASA Goddard for a specific coronal mass ejection coming from the sun in 2017. It turns out our spacecraft at Mars, MAVEN, observed this coronal mass ejection and the associated flares and their consequences for the Martian atmosphere. And so this is an initial reminder that flares are not the only energetic input to planetary atmospheres beyond the quiescent conditions. Flares are photons, but coronal mass ejections and solar energetic particles are massive particles, particles with mass, and fields as well. And all three of these inputs, photons, fields, and particles, can disturb planetary atmospheres. Flares are perhaps the easiest to see on stars that are not our own.
2 minutes.
So thank you. What did a flare do to the Martian atmosphere for a moderate flare in 2017? First, we see several orbits of data. When the spacecraft goes behind the planet, we can't observe the sun. So this gives you a sense of the orbit cadence. And during one orbit, the EUV flux increased greatly and then rapidly subsided. At the same time, as a function of orbit number, we can see the temperature in the thermosphere as recorded by the instruments on MAVEN. And at the time of the flare, the temperature in the thermosphere increased substantially. But 4.5 hours later, when we made the observation on the next orbit, the atmosphere had calmed down. So it's intense energy input, but it's very short-lived compared to some of the other energy inputs like coronal mass ejections and solar energetic particles that could last for many orbits at a time. So the flare heats things up and then calms down very quickly. So we've done some modeling on this entire series of events, and our model suggests that the flare increases hydrogen loss by a factor of maybe 5, and photochemical loss of oxygen by less than a factor of 2. But the coronal mass ejection increased ion escape by a factor of somewhere between 2.5 and 20. All of this is model dependent and ambiguous. And it also raises some questions about energy limited escape and how much of the energy from the flare is actually going into escape versus other places in the atmosphere. So the very last thing I can do in just one slide, and this is just a fun kind of interesting point. This is a conference about UV and stars and planets in the UV. So a point to make is that UV auroral emission can occur without magnetic fields, which is something that is obvious in retrospect, but not many people had thought about prior to several years ago. And that's because our experience with aurora is in Earth's global magnetic field, where you get current systems along the magnetic field lines that drive electrons into the atmosphere, excite the atmosphere, and as it relaxes, it glows. The magnetic field is essential to this process. However, on a planet like Mars or Venus that lack global magnetic fields, we still observe aurora, 2 different kinds actually. For Mars, this idea of diffuse aurora comes when solar energetic electrons go crashing into the atmosphere, excite the atmosphere, and as it relaxes, it glows. In addition, solar wind protons can do a charge exchange. They can neutralize as they're screaming towards Mars, and rather than being deflected around by the magnetosphere, can end up glowing as they decelerate as they head towards the Martian atmosphere. So this is maybe a caution that exoplanet aurorae may not always be a hallmark of the presence of a magnetic field. And I'm definitely at my time now. So this is just my last slide, and it recaps all 4 of the main topics, the main points that I was trying to make in our time together. Thanks a lot.
Thank you, Dave. We already have one question from Eugenia. Please go ahead.
The dog's name is Ellie. Thanks for asking.
Thanks so much, Dave. I really enjoyed that. So to your last point, is there any way by the strength of the UV aurora, say, that you could determine if there's a magnetic field or not? So let's say,
yeah,
is it particularly weak if it's unmagnetized and strong if it is magnetized?
Yeah, that's a good question, Evgenia. I think that the aurora is weaker. The non-magnetic field aurora is weaker, but it's happening on a planet Mars, for which even the aurora that happens in the small scale magnetic fields is also weaker. So, Mike may be a good person to better answer this question, but I think the global aurora is weaker, but when you integrate over the entire disk, maybe not weaker again. And when you imagine this happening on larger planets, I'm not sure what the answer to the question is.
Fascinating. Thanks.
Yeah.
All right, John.
Thanks so much, Dave. You talked about the induced magnetospheres. Is there sort of minimum requirements in terms of EUV flux or the extent of the atmosphere on the planet or the impacting solar wind flux for producing a induced magnetosphere?
Yes, there is. And that's a great question. So I think in order to obtain an induced magnetosphere, maybe the best way to think of a limiting condition is through the balance of pressure. The incident plasma has a dynamic pressure, rho v squared. And if the planet can't supply enough pressure to offset that, then the stellar wind will go crashing right into the planet. So the planet could supply that pressure in the case of Earth through magnetic pressure from the magnetic field. In the case of an induced magnetosphere, ultimately that pressure is coming from the ionosphere itself, the thermal plasma pressure, NKT. So if you can't get enough NKT in the ionosphere, then the stellar wind is going to come all the way down to the atmosphere. This doesn't happen ever at Venus, but at Mars, it can happen. You can push the induced magnetosphere. You can overpressure. The solar wind can provide an overpressure for the entire system.
Great, thanks.
All right, we have time maybe for, well, we'll have a break later, so we can go for 2 other questions. Please go ahead. Timothy was the next.
Sorry, I have one question. Sorry, this is Manuel Hernandez. I don't know if I can make the question.
I can wait. Go ahead.
Yes, it's very, very short because I saw that in your presentation, you mentioned that in the third point that you found a strong solar flare and without not so high response, one X-class solar flare, if I remember well. So in my experience, this can happen, for instance, in the Earth ionosphere, when the solar flare is the sunspot group happens close to the border, far from the center, because the solar atmosphere strongly absorbs UV, but not absorb so much the X-ray band. So my suggestion is, in such flare, if I understood properly, please check the location of the sunspot group which generated the flare, if it is close to the limb or not. Thank you.
Understood. Thanks.
Timothy?
Sorry, can I just butt in for 1 second? Everyone, sorry, Timothy. I just want to give everyone some warning that we are going to start in 10 minutes on the next session. We can keep talking. I'm loving this conversation. I have nowhere better to be, so we can keep talking, asking questions as long as Dave agrees to that. But we will be starting in 10 minutes on the next session. So if you need a break, please step away.
Either way is fine with me. I'm also happy to answer questions in chat if people want the break, and I'm fine with either.
Whatever you want.
So one of the indicators we have for modification of an atmosphere, or the chemical inventory of volatiles, is the enrichment of heavy isotopes. And we're just starting to get reliable measurements on heavy isotopes of oxygen and carbon in the atmosphere of Mars, for instance, and we're still lacking that information for Venus. Can Maven give us any information on the relative escape efficiency of O18 versus O16 that we can use to help deduce the primordial atmospheric density on Mars?
Yeah, good question. And the answer is I'm not sure. There are folks working on D to H, and there are folks working on argon isotopes. So I would imagine that it's possible with Maven observations to do work with O16 and O18, but I'm not sure of anyone on the team who is doing it. Mike Chaffin, if you know, feel free to chime in. Maybe it's not possible, but I think that it should be.
I don't know that we can do it. So I think it would be difficult to make a measurement of the different isotopes, but you could use the same photochemical modeling technique that Rob Lillis has used to model the photochemical escape to make an estimate for the photochemical escape of the isotopes.
I think you would run into a lack of cross sections for those dissociative recombination reactions that drive the escape. That's my guess, is what would limit the ability to extract knowledge from our MAVEN observations.
Okay, thank you.
All right, let's Melody, you can ask your question.
Hey Dave, thank you for the really awesome talk. This is a bit of a follow-up to Evgenia's question. Evgenia, are you there? All right, I'll like Slack her and tell her what she says later, what you say later. But I'm just curious if a planet, depending on how a planet is magnetized, would you expect there to be a spatial variations in those two different, like the diffuse aurora and the proton aurora?
Yes, yes, I would. So if you could somehow resolve where the aurora were coming from, then a magnetized planet should have the aurora coming at the two magnetic poles at the boundary between the open and closed magnetic field lines, because typically the particles are energized in the magnetotail of the planet and come rushing up the magnetic field lines and impact in the cusps.
Yeah.
For an unmagnetized planet, then you would expect the aurora to occur across the entire disk.
So Mars has, like, it's not unmagnetized. It has, you know, that sort of lumpy crustal field. Like, is there any spatial variation just from the lumpiness of that field?
Yeah, so I mentioned just two types of aurora at Mars, and those were the two that MAVEN discovered happening that don't require magnetic fields, but known before MAVEN ever got there, it was known that aurora occurred in those crustal fields of Mars. And so in these small scale magnetic fields, you get very localized aurora as well. And they can, they're relatively faint because it's a small region, but the energy of the particles that are creating the aurora can sometimes approach the same energies that cause Earth's aurora as well. So they're just over small patchy regions. And MAVEN observes this third kind of aurora as well.
Okay, cool. Thank you.
Yep.
Next up, we have Vladimir. Just remember that we will be back in 4 minutes. So please go ahead, Vladimir.
Yes, hello everybody. Yes, thanks Dave for a nice talk. So I just want to comment on the question that Eugenia Shkolnik asked about the the effect of the solar wind on the magnetized atmosphere. So the point is that when depending on the orientation of the BZ component of the magnetic field, of the solar wind magnetic field, we can have the magnetic reconnection, and this magnetic reconnection can excite auroral electrons. So the statistical studies of the Earth magnetosphere show approximately linear correlation between the solar wind driver and the energy in the solar wind and the total energy flux in the accelerated electrons that create aurora. So that's basically would be a comment to answer this question.
Yeah, thanks. So that's for maybe energy and brightness of aurora in magnetized planets. And then the energy and brightness of the unmagnetized mechanisms is going to depend to some extent on the energy of the incident particles that are depositing in the atmosphere. Yeah, thanks, Glenn.
Thank you. Next up, we have Amanda.
Hey, Dave. What about Io's auroral emissions? Where do they fall in your scheme of things?
Oh, that's a good question.
It's not magnetized.
No, but the particles that are being deposited are following strong magnetic field lines into the atmosphere. And they were accelerated on those magnetic field lines.
Jupiter's.
Yeah, on Jupiter's. So in Earth, the acceleration of the particles happens inside the magnetosphere. You need the magnetosphere there to create the acceleration. For Io, you don't need its intrinsic magnetic field or lack thereof. You know, that doesn't play a role in the acceleration. Instead, all that work is being done by Jupiter. So it's in a gray area between the two.
Right. Okay. Cool.
Yeah.
Thanks.
Thank you. All right, I will take a break of 2 minutes. If you want, you can continue discussing. I'll be right back.
Thanks so much, Leo. I'll take over. Did Vlad ask this question yet?
Yes, I did.
You did, because I stepped away for a minute too.
Well, that was a comment to your question, actually.
Okay, maybe you could type it in the chat for me. I'm curious.
Sure. Yeah, well, yeah, thanks.
Thanks. Good to see you or hear you. Gosh, thanks so much, Dave. That was a really interesting talk.
Yeah, thanks for having me.
Yeah, thank you. I know you had a busy day bouncing back and forth.
I should be here the rest of the time, but I had a PhD defense right before this. So I had enough time to catch sort of 2 talks before mine, which was enough to sort of figure out how things were working.
Excellent. Great. Yeah. Thank you.
All right, it's 11:55, so let's return from the very short break. Next up, as far as, all right, I see the speaker. The speaker is Zara Brown, and she will give a contributed talk. And you have 7 minutes, and I'll give you a heads up when you're 2 minutes from the end. So please go ahead.
All right, let me go ahead and share my screen. Let's see, you guys can see that?
Yep.
Okay, great. Well, thanks for having me. I'm going to be describing my research analyzing FUV and EUV data from the Cassini Grand Finale suite of occultations. So I know we've got a lot of exoplanet people here, and I'm going to make the case that studying our solar system giant planets is a great way to understand those giant exoplanets that we've discovered around other stars, because it's impossible at this point to characterize them in as much detail as we can for Saturn. And it's given us a lot of interesting information. So the ULLYSES instrument observed in 2 channels simultaneously. So in the extreme ultraviolet channel, it probes the thermosphere, and from that we can get densities of molecular hydrogen and temperatures. The FUV channel probes lower down in the mesosphere and can detect light hydrocarbons, including methane, acetylene, ethylene, ethane, and benzene. So the mesosphere is an important part of the upper atmosphere. It is where photochemistry begins with the breakdown of methane by photolysis. So at Saturn, I know this isn't the case on all planets, but at Saturn, the photodissociation of methane does not significantly impact its density, and it can therefore be a good tracer of dynamics. So I'm showing you the location of the homopause here. It's the point where below which all of the species that we're seeing in this plot on the right are well mixed, and above that point, species diffuse based on their own scale heights. So if we had local downwelling, for example, that would bring, for say, methane poor gas from above and bring it downwards, and that would depress the location of the homopause. And the reverse would be true for upwelling. So the location of that homopause is a good indicator of relative upwelling or downwelling in the atmosphere. So the grand finale campaign was a really unique observing campaign and really important. So the plot on the right shows the latitude coverage of occultations taken by Voyager and by Cassini over time. And we've had a lot of observations, but you can see the black points at the bottom, which are showing you the grand finale observations, are really unique because they're probing the atmosphere from 86 south to 86 north, providing broad latitude coverage and pretty good spacing as far as density. And since each of these gives us a profile in altitude, taken together, we can give a 2D snapshot of Saturn's upper atmosphere using these data. So I'll start by doing a very brief overview of our methods for retrieving the H2 and temperature data using the EUV data. So stellar occultation fundamentally is when here we use a bright ultraviolet background star, and that is occulted by the atmosphere through various lines of sight. So that gives us transmission profiles as a function of wavelength and altitude. And using those, we can do an iterative forwarded model fit to transmission to give column densities as a function of altitude, which we then invert to give number densities. So by assuming hydrostatic equilibrium and an ideal gas, we can integrate that to give temperature as a function of altitude, which I'm showing here on the right. I hope that I'm coming through. My internet seems to be a little sluggish, amazingly. Okay, great. So this has helped us answer well, answer is too strong. It's helped really shine a light on a long-standing question in planetary science, which is the energy crisis. And doesn't seem like my slide is advancing. So that's good.
Your audio is cutting a bit.
Goodness. And my page is unresponsive, so that's great. Yeah, okay, I think I'm gonna try, I wonder if I can take my video off, or maybe my internet is done being not good. Okay, how's that?
I can see your next slide.
Okay, great. Yeah, sorry about that. So the energy crisis, simply stated, is that the temperatures that we observe at all latitudes are hotter than we would expect by solar heating alone. So there must be some additional heating mechanisms. So there are several that I won't go into, but Joule heating deposited at auroral latitudes, there's enough of that to heat the entire thermosphere to the temperatures that we observe. However, previous studies have suggested that equatorward redistribution was entirely prevented by Saturn's strong Coriolis force. That's not the case, but it is inhibited by those forces. So what we see, so on the left here is a 2D plot of temperature in the thermosphere, which has been interpolated from our 23 stellar occultations at varying latitudes. That's kind of why you see this jagged appearance at the bottom. It's just an artifact showing you the bottom, the deepest pressures we can probe at each latitude. But what we see from this is that compared to models that suggested that equatorward redistribution would be difficult, we find that the peak temperatures are cooler and they're located at lower pressures and lower latitudes than previous models had predicted. So that's suggestive that heating may be occurring right at these auroral latitudes. We can also look at the gravitational potential gradients that arise from the observed temperature and densities and infer winds from those. So at the right, I'm showing you wind speeds as a function of latitude from our data, which is the solid lines, compared to the model, which is the dashed dotted lines. And compared to this Saturn thermosphere ionosphere model, we're showing that the observed winds or the inferred winds are slower, broader, and closer to the equator than what that model had predicted, meaning that the barrier to redistribution is less than we previously thought. So taken together, these results support the idea that auroral joule heating with redistribution to lower latitudes is a major contributor to the observed temperatures. So I'm going to just briefly also describe results from analyzing the FUV data. The process is pretty similar to how we retrieve data in the EUV, with the major difference being that we here simultaneously fit 5 hydrocarbons at each latitude. So this plot on the left shows you the optical depth, with the black being the observed, and then the contributions from each of these varying species. So we invert then column density in the same way to produce number density profiles. And at the right, I'm showing you the results from one analysis at 42 degrees north latitude with density profiles for our 5 light hydrocarbons. So with that, I have been recently fitting a model atmosphere to the methane and molecular hydrogen data. And so I'm showing you that model at the right, which gives volume mixing ratio on the x-axis and altitude above the 100 millibar on the y-axis. And so by assuming that the eddy mixing coefficient, KZZ, is constant, the effect that that has on the model atmosphere is that it moves the point of the methane homopause up and down, basically, among other things. So by selecting the best fit KZZ for each of our occultations, I then plotted what that KZZ would be as a function of latitude here on the left. And you can see that the highest KZZs needed for a good fit are here at the low latitudes, right near the subsolar point, around 30 degrees north. And that KZZ drops as you go towards the poles, particularly in the southern hemisphere, which is the winter hemisphere for these data. So that suggests relative upwelling at low latitudes and relative downwelling near the poles. So further work is needed to constrain that, and we'll be working with modelers to give that a full treatment in the future. So since I'm here with so many exoplanet scientists, I noticed that there's a paper that just came out on AstroPH that calculates the transit depth of Titan using one of the ULLYSES occultations. By integrating absorption over radius. And they give this plot at the left with several features identifiable there. And so I performed a similar integration using a formula from Brown et al. 2001 to show what Saturn might look like if we saw it as an exoplanet, if we lived on another star system. So the plot is sort of similar in some ways to what Tribbett et al. Find. We can see some of the same features, including this like broad increase in transit depth where methane absorbs. We can see some distinct features from acetylene there around 1500 angstroms or 150 nanometers. And you can see clearly in the Titan occultation, this methylene features around 170 75 nanometers. They're not as pronounced at Saturn. But we can also see these very spiky Lyman and Werner electronic bands in our calculation of the data. So the transit depth that we're showing here is around 0.7%. And so it seems to suggest that H2 could be detectable in atmospheres of other planets, but I'm not really an expert on that. I'm really looking forward to the atmospheres talks later in the conference. So just to conclude, stellar occultations are a wonderful observing tool that can provide density, temperature, tell us about photochemical products. And by taking a series of these with latitude, we can get a 2D snapshot, which is the only way that we can really understand things like circulation in the upper atmosphere. So that would be really interesting to do, for example, at our ice giants, Uranus and Neptune, which are not well understood in terms of their upper atmospheres. And it may be possible to detect hydrogen, Lyman, and Werner electronic bands in exoplanet atmospheres. So that's my last slide, and I'd be happy to take questions.
Thank you, Zara. Unfortunately, we don't have time for live questions, so I encourage you who have questions to ask in the chat, and we'll go directly to the next talk.
Thank you.
So next up we have Go Murakami.
Yeah.
Can
you hear me?
Yes, and I can see you too, so I can take it over. Just a quick reminder. Remember to turn, if you please turn on your video when you want to ask a question. All right, take it over.
Okay, thank you. So I'm Go Murakami from JAXA, Japan. It's now 4 a.m., but I try to do my best. Okay, so today I'd like to introduce briefly our future mission concept, future ultraviolet space telescope in Japan. Now the name is Raptor, so today I briefly introduce. So actually we have several heritages of UV observations in Japan, so especially the solar system science. For example, we have several instruments in space for observing Earth's upper atmosphere, and also we brought some instruments to the planets and moon. Especially now our UV detector is on board the Bepi Colombo or MPO spacecraft. And so now we think the UV observation is one of the core techniques in Japan. And also we have one space telescope in UV range. The name is Hisaki. So I briefly introduce. So Hisaki is the first space telescope dedicated for the planetary science and solar system bodies in UV and FE range from 50 to 150 nanometer. And so it was launched in 2013 and still working. The mission is extended to until next year, sorry, to 2020, to March. And this is the optical layout of Hisaki Space Telescope. So very simple, or just a 20 centimeter diameter of primary mirror and one spectrograph with grating and MCP detector. And the strong point of Hisaki is the capability for long-term and continuous monitoring, especially for the Jovian ioplasma torus. So here is a snapshot taken by Hisaki. The ioplasma torus is here. And we performed the long-term monitoring. This is one example for 6 months monitoring of the activity. And we successfully detected the change of the Io's volcanic activity. So some volcanic activity started here and go to the peak and go down like that. So this is the first time to detect the whole Io's volcanic activity, but our instrument was not so high effective area and high spatial resolution. So there are still many open issues due to this lack of the performance. And now we are participating in the international collaboration for UV Space Telescope. So, for example, here is the World Space Observatory Ultraviolet. It's a Russian lead space telescope in UV. It will be launched in 2025. Oh. And it has a 1.7 meter diameter. The spectral range is here, and the orbit is just geosynchronous orbit. So it's very important for because outside of oxygen geocorona, so we can perform the oxygen observation with very less contamination from geocorona. From Japan, we will provide one spectrograph. Name is UV Specs. Lead is single camera. Unfortunately, he planned to present tomorrow, but he canceled, unfortunately. So here just a one-page slide to introduce them. And now it's a project in JAXA, so phase A2, and it will be soon phase B. And this instrument is focused on the detection of Earth-like exoplanets. It's upper atmosphere in hydrogen and oxygen with the transit observation. And here's our overview of our concept study. It names Raptor. So actually just started, we have just started our concept study end of last year. And we are targeting the JAXA M-class category. And currently it's still pre-phase A1A, and the target launch is 29. And actually, so the main part of our team is for the solar system science, especially for the detection of water plumes from icy moons. But also we want to understand the interactions between the moons and planets in Jupiter and Saturn system. And of course, as today's presentations, the upper atmosphere or exospheres of Venus and Mars are very important target also. But not only the solar system science, we are expanding our science targets to the exoplanets, like especially the habitable, the Earth-like planets in the habitable zones around M2 orbits. And also we have some colleagues to work together for the astronomy, especially the nearby universe, to test the structural formation scenario of the lambda cold dark matter model. And also the multi-messenger and time domain astronomy is also the target of this mission. So this is a specification of the Raptor mission concept. So the primary diameter is 60 centimeter, and we want to achieve the more than 350 square centimeter of effective area. And we also want to achieve the high spatial resolution of 0.1 arcsecond. And the spectral range is like that, and the spectral resolution is 0.01 nanometer. So it's 100 times higher sensitivity and 100 times higher spatial resolution than Hisaki. So preliminary design is like that. So the optical layout is the Cassegrain telescope with effective focal length of 36 meter with 60 centimeter mirror. And now we plan to bring two major science instruments. One is a spectrograph with simple optical layout, so slit and toroidal grating and MCP detectors. And also we plan to put the wide field of view imager with 4 large format MCP detectors array like that. And also we are now studying several supporting and option instruments like that. So we are now developing several key technologies. So especially I'm working on the detectors, so like the funnel type MCP detector with higher sensitivity, about 2 times higher than the conventional usual MCP detector. And also, I'm working on the CMOS coupled emissivity detector to achieve the wide dynamic range and the high resolution, like that. And also the gratings and mirrors, now we are working on for the future mission. Okay, so this is a summary, the specifications like that. And yeah, our concept study is just started, and we are welcome to any science request, or we are so open to hear from you. So if you are interested in, please contact us. Okay, that's all. Thanks.
Thank you, Go.
Yeah.
All right, so we're open for questions. We have time for a couple of them. But if not, I have one very quick one. It's about the WSO UV spectrograph. Yeah. Is it going to be focused on exoplanet and planetary science, or is it going to do everything related to cosmology?
Good question. So actually, the design is dedicated for the exoplanetary atmospheric science. Mm-hmm. But if there are any proposals, it's also you can use you can propose any science observations if it matches your objectives.
Right.
Yeah.
All right. Evgenia?
Yeah, thanks so much. Thanks so much for waking up in the middle of the night to do this. I really appreciate it. Exciting new concept. So question, you have a large range of scientific topics that you want to cover, from solar system, right, exoplanets, nearby universe, and so on. Do you have a distribution of time that you want to allocate in your mission to these yet, or is that still something up for debate?
Actually, it's still under discussion because we are just started. But so we are having some kind of baseline plan for divide our observation time. Mm-hmm. And currently, it fits in our mission timeline. So of course, in the future, we will sophisticate them. But we can still open. We have still open time for the future science proposals.
But you would consider solar system science your top priority? Are these ordered in priority, or?
The priority is also still under discussion. But for design point of view, the highest difficulty is the solar system targets. So currently, we have a top priority for the solar system bodies.
Gotcha.
Especially as a resolution point of view, yeah.
The spatial resolution, that's their biggest challenge.
Exactly. Yeah.
Got it. Cool, thanks.
Thanks.
All right, thank you. There are no further questions. We can go ahead with the next talk. It's a contributed talk by Vincent Yu. You also have 7 minutes, followed by 3 minutes of questions. So please go ahead.
Yeah, can you hear me now?
Yep, I can also see your screen.
All right, everything works fine. Okay, great. Yeah, thanks. I'm excited to give a talk today to you guys. I'm going to be talking about the observation of Juno or Jupiter UV aurora with the Juno spacecraft that is currently orbiting Jupiter. So Juno is a NASA New Frontier mission, which is currently on a 53-day orbit around Jupiter, a polar elliptical orbit. So this orbit that you see here, and it's been orbiting Jupiter since 2016. I work at Southwest Research Institute, and there we developed an instrument called Juno UVS, which is actually a photon counting UV spectrograph operating between 68 and 210 nanometers, with a spectral resolution as good as 1.2 nanometers. One of the specificities of Juno is that we are spinning spacecraft, meaning that we are scanning across Jupiter, and we can build, by co-adding successive spin of data, we can build a global coverage of Jupiter's UV aurora. This animation that you see here at the bottom shows you how, by co-adding consecutive swaths, we can build a global picture or global spectral images of Jupiter's aurora. So the goal for UVS was actually or the Juno payload was to explore the Jovian magnetosphere, and UVS was designed to provide auroral context images for the in-situ particle instruments on board Juno, in order to correlate the precipitating particles with the UV aurora they actually create. I'm kind of excited to talk about these very recent results that we got that was presented at AGU in 2017 and got submitted recently, which actually show the clear dichotomy in the local time emission of dependent emission of Jupiter's UV aurora. So on this plot here, you see two images of Jupiter's aurora recorded at roughly half a Jupiter rotation apart. So the left plot shows the UV brightness, while the right plot shows the color ratio, which is kind of a proxy for the depth of the auroral emission, the depth at which they're emitted in Jupiter's atmosphere. So you see here a polar projection. So the top plot we're recording when the northern aurora was mostly in the night side of the planet, where you see my cursor. This is a terminator, and the sun is towards the bottom. And the bottom plot shows when the aurora is actually mostly located on the day side. So you have the terminator right here and the sun again at the bottom. And so the main takeaway here is that the innermost aurora, that we also call the polar aurora region or polar cap, kind of shuts off at night, as you see here on the top plot. And so we're still working on the explanation for those to explain this effect. The two main hypotheses right now are the fact that when the aurora is on the day side, you have higher ionospheric conductance, which then leads to more auroral emission. And the other hypothesis is the magnetospheric control of the auroral emission. So the team is actually still working on those two explanations. So again, UVA's main goal was to provide context images for the in-situ particle instruments on Juno. So typically what the team does is providing images such as this one, which shows the northern aurora in false color scheme, that we then compare to the electron distribution measured by the different in-situ instruments on Juno, such as the JEDI or JADE instrument. And we compare that to the magnetic trajectory of Juno, which is represented here. So the middle panel here shows you the azimuth distribution, electron distribution measured by JEDI, where you clearly see in some part of the trajectory of Juno electrons that are aligned with the magnetic field of Jupiter. And the bottom panel shows you the energy flux upgoing versus downgoing into the planet along the trajectory of Juno. So there's a lot to unfold into this, and I'm just going to talk about one of the surprising things we discovered, which is that when we actually cross over the polar region right here, what we saw was mostly upgoing electrons with a broad energy distribution, which is kind of surprising because you would expect that when you have auroral emission, this is downgoing electron that triggers this auroral emission. And we think the acceleration region is actually located to lower altitude, below the spacecraft below when Juno flew, which might be attainable in the extended mission of Juno.
2 minutes.
We also discovered a kind of new type of auroral emission characterized by faint circularly expanding auroral feature, which I'm gonna illustrate here in this short 3 or 4 spin video, which are expanding on the order of a few kilometers per second. And based on the spectral characteristic of those, they are created by electrons precipitating in the range of 80 to 160 keV and mapping to the outer magnetosphere, because again, those features are located in the polar auroral region, meaning that they come from the distant magnetosphere. potentially the interaction region between the solar wind and the Jupiter's magnetosphere. We also discovered transient UV events away from the auroral region. So what you see here is two images of one spin of data. We discovered some transient flashes here that we identified to be similar to transient luminous events that we observe on Earth, which are related to lightning activity. We also discovered one event that is spectrally consistent with black body emission, potentially from a bolide colliding into Jupiter, again, away from the aurora. So again, this is one spin of data right here. You see the aurora here with a different color scheme. I will finish on this slide because I think this goes a little bit beyond the strictly speaking UV aurora of Jupiter, because UVS has done regular stellar calibration, and because Juno is a spinning spacecraft, we've been recording a very large amount of UV observations, stellar UV observations. The bottom plot shows here a combined exposure map for all the stellar observation data we got during the entire mission so far, with combined exposure time up to an hour. And the top plot shows the corresponding UV brightness that we assembled, and we covered more than 99% of the sky so far. And again, remember that every pixel here is a spectra from 68 to 210 nanometers. So it's a pretty incredible data set we have that still needs to be properly reduced, assembled, and archived. So thanks for your attention. If you have any questions, I'll be happy to answer, or if not, just feel free to email me.
All right, thank you, Vincent. We have time maybe for one very quick question.
Can I ask a question? Oh, quick.
Go ahead.
Thank you very much, Vincent. This last bit is super interesting. Just make sure I understand. You have 1 full hour of cumulative integration at this wavelength range of nearly the whole sky. Is that right?
Yes. Yeah.
And with what time resolution within that hour?
It depends. This actually uses many data sets combined together, and the smallest temporal resolution we have is 30 seconds because the spacecraft spins at 2 RPM, meaning that if we observe a stellar source, it's going to be on a 30-second cadence. So the signal to noise ratio per spin is very low, although on some stars it could be okay. But yeah, we have a long baseline of observations that needs to be explored.
And it's a spectrum at what resolution at these wavelengths?
So as I said, the best resolution we get is 1.2 nanometers.
Okay. Thank you. I missed that. Thank you.
Yeah.
Okay.
All right.
Cool.
Thank you. Unfortunately, we are running over time by 7 minutes, so we have to go ahead for the next talk. But I encourage you to leave questions in the chat if you still have them. And next up, we have an invited talk by Watt Harris. You will have 15 minutes plus 5 minutes of questions. So please go ahead. I can see you already.
Okay. Hi, everybody. I was invited to give a talk about the general topic of UV observations in the solar system. And I thought it was daunting when I started, and I vastly underestimated how daunting that was in a 15-minute talk. So what I'm going to try to do here is kind of talk a little bit about the considerations for observations of this type in the solar system, put a little perspective on things, do a little history, and then do a rapid fire of some basic examples of the sort of things that we see, some of which have already been covered in other talks at greater depth and better detail. So if I'm underselling your particular object or your particular area of expertise, feel free to ask me about it afterwards. I may or may not be an expert enough on that area to be able to say too much about it, but I apologize in advance if I'm not going deep enough.
All right. Well, sorry, we don't see your slides if you have
don't.
I don't.
All right, let me try escape. Do display.
Do you remember to share the screen?
Yes, I thought I did. Maybe it was the other one was still on there. Okay. It now?
I cannot see. All right, now I can see. All right.
Okay. Let me.
All right, I can see. Perfect.
Are you seeing the full presentation now?
We are seeing your presentator notes. If you can swap them.
Let me try this. How about now?
I am still seeing your presentator notes. It should be swapped because right now I'm seeing
at the top. Walt, go up to swap
displays.
displays.
Swap displays. Yeah, true.
Hold on.
You see swap displays at the top of your presenter screen?
Top left.
No, I don't see them.
It's a little bit to the
right.
Oh yeah.
You briefly hovered your mouse over it. It's the third button on the top left.
Yep, right there.
Yeah, there you go. Yeah, just click.
Well, I can tell you why I can't see this is because all of the Zoom buttons are over it.
Oh.
How do I get rid of this? I don't know how to do it.
Maybe if you stop sharing and then screen share again.
Yeah, let me try this. No, the problem is it's covering that particular button.
Right.
Oh.
So I can't hit it. Figures.
You can help guide you.
All right. Well, I mean, I can get to it. It just doesn't let me.
You can
mutes me instead.
And there should be an option to end presenter view.
Okay.
I hear a cat complaining. I can see your screen. Yeah, I can see your screen. All right, perfect.
Sorry. All right, I'm really sorry about that. Well, my daunting task just got more daunting. Okay, let me fly through this as fast as I can. When we're talking about the solar system in terms of energetic processes and ultraviolet observations, we're really talking about the sort of general topic of the sun-planet connection for the most part. And in that perspective, the solar system really is a collection of sort of independent systems that are enclosed within the heliosphere with the sun controlling the outside environment. And while the solar continuum emission is obviously dominant for the overall energy budget for virtually everything in the solar system, with the exception of infrared emission from the giant planets, solar activity and solar UV radiation are what drive conditions in the very thin atmospheres and the upper atmospheres of the planets and in planetary magnetospheres. Location is key in this regard, in that the farther you are away from the sun, the lower these effects are going to be, and also the harder it is for us to be able to observe them. And unlike some other astronomical disciplines, as we've talked about, Robotic exploration gives us an opportunity to look at these individual systems from multiple perspectives, and that vastly improves our ability to understand them. Normally, we don't think about this in terms of solar system, but the sun is really an essential element of every study of energetic processes and upper atmospheric conditions, because solar activity drives both the solar wind, the solar magnetic field, the intensity of solar UV and EUV radiation, and hence drives the conditions in every one of the locations that we might go to. It does us little good, well, not no good, but less good, to observe these objects without knowing what the sun is doing at any given time. And so the presence of a vast array of EUV monitoring satellites from SOHO to SDO has given us that opportunity to put those things in context through detection of flares and CME events and things of that nature. Going back a little bit into a bit of history, I want to kind of just talk about the Earth for a minute. The Earth was really the first planet that was studied in the UV, and it was really because it was the only planet we could study in the UV early on. In the late 1950s, we began launching sounding rockets with UV photometer instruments, and we followed those with the OGO series of satellites. And those were used early on to determine the contours of the Earth's geocorona and aurora, and to detect airflow emission from hydrogen, oxygen, and several other species in the Earth's atmosphere. Later, when we went to the moon with Apollo 16, the Carruthers UV telescope, which was essentially a Schmidt telescope sitting on a tripod pointed by an astronaut, was our real first opportunity to take a look at the Earth's corona as an integrated system, as an image. And they were enormously successful at doing this. They characterized the Earth's aurora, observed the equatorial anomaly, and measured atmospheric scale heights of hydrogen, helium, nitrogen, and oxygen, and really started all of the techniques that we use today to observe the solar system in the ultraviolet, and they did it with a microchannel plate in front of film. So we don't get to complain about our technology, except that I will later on. So a byproduct of those early observations was that they detected that there was an excess in emission behind the interplanetary hydrogen, or behind the corona, which we now understand to be interplanetary hydrogen. And what this material is the interstellar medium passing through the solar system. And it's the neutral component of that. And it is now subsequently been mapped multiple times by SOHO for its spatial extent. And it is a substantial background. And also early in the mission, it was mapped for velocity using a hydrogen absorption cell. It's also been mapped for velocity using ULLYSSES, the IUE, and HST, and other sounding rockets, including some I've flown. It's not necessarily a part of these connected systems, but the interplanetary medium contains the signature of the heliopause via charge exchange at the hydrogen plasma pileup region on either side of the boundary. And so it is a measure of the contours of our environment. So now I'll move on to a planetary system that is kind of a good example of the sort of integrated collection of phenomena that are all related, but are interesting individually. The Jupiter system is really the belle of the ball when it comes to this. Auroral emissions from Jupiter in the form of neutral and atomic hydrogen emission excited by electrons has been observed for more than 40 years. It was discovered by Voyager, monitored by at least 2 people on this call for a big chunk of the 40 years that we've known about it using IUE. And more recently, it has been imaged in 2 dimensions by HST and Juno, as we just had described in the last talk. Within the system, the Galilean satellites occupy a role as sort of a microcosm, which you can see in these images, but I'll get to in a little bit. At the lower right down here is a classic spectrum of Jupiter's aurora. It shows the bright Lyman alpha emission and then emission from the Lyman and Warner bands. Typically, we have studied them by looking at the intensity of the bands and also their ratio as a function of rotation state on Jupiter, because the presence of methane in the atmosphere absorbs a portion of the auroral emission. The magnetosphere of Jupiter itself is really dominated by the presence of Io. Mass loss from volcanic activity is driving this by becoming ionized and getting grabbed by the Jovian magnetic field and accelerated into a vast co-rotational torus of charged particles that stream past Io at tens of kilometers per second and sputter more material off its surface. At the lower right here, you can see auroral emission from Io as a function of different species, as obtained with STIS early after it was installed. And you can also see the bright bars are the torus itself. At the lower left is the extent of it in different wavelengths of the EUV as observed by Cassini UVIS. And what you can see is this large toroidal plasma distribution. It's not perfectly co-rotational and material isn't there forever. And so torus plasma expands outward into the rest of the magnetosphere. Partly due to the fact that this plasma is out there and due to the fact that Ganymede has its own magnetic field, we are able to see auroral emissions at both Ganymede and Europa. Ganymede directly connects into Jupiter's magnetic field through its own magnetic field itself. Europa, like Io, interacts with Jupiter via the current of charged particles moving past at high velocity and sputtering material off its surface. These connection points feed back into the auroral oval in the form of what we call footprint emission, which you can see over here from Io, from Europa, and from Ganymede. And this has now been seen also from Enceladus at Saturn. These satellites that produce substantial amounts of material and form rings generally tend to also interact with the upper atmospheres of the planets that they orbit. An important additional point to keep with this is that all of these footprints at Jupiter are southward of the main auroral oval. Early on, we believed that Jupiter's aurora was dominated by Io entirely, but the location of the footprints relative to the oval tells us that the solar wind is still a major factor in auroral activity there. Another general point about ultraviolet radiation is that it interacts with most of the composition of planetary atmospheres, which means that photochemistry and ionization are important for upper atmosphere composition, energy balance, current structures, and dynamics. The mass of these regions is comparatively small compared with the rest of the atmosphere. And so they are greatly affected by absorbing energy from photon processes. Attenuation and scattering of ultraviolet emission that is coming in tends to isolate these regions in UV imaging. So we look at the area above where the attenuation occurs. And we can see this as we move from one part of the UV into another part of the UV, the formation of hazes, changes in the band structure of Jupiter, etc. We also can see this in other planets. There's the enhancement of cloud structure and superrotation at Venus from absorbers below the level being observed. And also we can see scattering in the atmosphere of Jupiter producing a non-thermal emission feature, what they call the Lyman alpha bulge, from massive scattering in the upper atmosphere of Jupiter. And the other advantage is that absorption in stellar and solar rock rotations, as was previously pointed out, can be used to map atmospheric profiles at different locations. And I show here a solar rock rotation doing this at Pluto, which is just absolutely amazing that we've been able to do that. Final topic that I'll cover are small bodies or comets. Comets aren't atmospheres per se, they're basically steady state exospheres that continue to release volatiles. Almost all of the volatiles released from comets are rapidly photolyzed within a few days of being produced. And that means that the characteristics of the coma change rapidly as a function of distance from the object. And it is important to understand the total production rate of parent molecules and also the rates at which they are photolyzed and the rates at which they are expanding away from the nucleus in order to really back in exactly what's coming off the surface of a comet. The ultraviolet is a particularly important wavelength range for studying this because it has a number of important molecular signatures, including hydroxyl, which is a daughter of OH, and CO, which is produced on its own and also is a daughter of CO2. And by looking at the emission lines in the far and near UV, we're able to determine things like the CO-CO2 ratio and also the water to CO-CO2 production rate ratio. Thank you. The line brightnesses individually are sensitive to production rates, chemical processing, and impact processing. In addition to spectroscopy, we can use wide field UV imaging to actually trace the expansion velocity and the mass budget of comets, because eventually everything that comes off a comet turns into carbon, hydrogen, nitrogen, and oxygen. And by measuring the total production rate of those and also their radial distribution before they become ionized, we are able to back in the production rate. In the case of hydrogen from SOHO, we were able to also look at high resolving power at the non-thermal velocity distribution, which contains signatures of the photolization process from water to hydrogen gas. And finally, at the left here, I show a spectral image taken with the GALEX satellite that shows how overlapping comas exist of multiple species simultaneously. And this can sort of be used to map multiple scale lengths simultaneously. So don't have a whole lot of time left. So I think what I want to do is just kind of skip to the future. The UV is really a workhorse spectral range for understanding processes inside the solar system at the levels of upper atmospheres out into the heliosphere. But as we all know, the fleet of instrumentation is really old or is based on technologies that were developed more than 30 years ago. We've made many of them better, but they are not fundamental advances of the kind that we were seeing in the first 30 years that we were studying ultraviolet emissions.